Might as well get started. Thank you for joining us again. Yesterday was a great session, kind of laying out a basis of in the history of risk-informed decision-making. Today, our focus really is going to be largely on benefit cost analysis for projects. And this stems from an effort that FEMA is considering with the National Dam Safety Review Board to add some sort of benefit cost analysis to the high hazard potential dam grant process to justify the projects that are being undertaken under that grant program. It's still in a state of flux and still debating the pros and cons and trying to come up with a simplified methodology. But we thought it would be a great opportunity to learn what's out there in terms of the state of the practice. And so we'll be getting into that. We do have, unfortunately, we've lost a presentation this afternoon on that topic. Steve Costello from the city of Houston, who's going to be speaking later on this afternoon. He is in Houston. They are without power. He's unable to make that presentation. We'll be showing Charlie Cobb's presentation in that place today. I think it's 3 o'clock. And also, but you could still view Steve's PowerPoint presentation for what it's worth in the slide deck. Alicia, I'll turn it back to you for administrative.
Yeah, great. Thank you, Jim. And good morning, everybody. Welcome back. Just a couple of reminders. We would like everyone to fill out their evaluation sheets daily so that you don't forget. So please make sure that your 5 from yesterday are already filled out. As we've noted just a couple moments ago, to ensure that everyone understands who they need to be evaluating next, we will put that information into the chat at the beginning of each presentation, whether there is an evaluation to fill out, and if so, what the correlating titling is. And it looks like someone is messing with the pods again, so please don't play with those. I don't know why that keeps happening. 1 second while I try it. Okay. Christina, would you mind fixing that for me so I can keep going? So with the Adobe Connect pod usage, I just wanted to remind everyone, please put any of your technical issues that require assistance in the admin technical pod, and then the actual questions for the presenter in the Q&A pod. We do have question moderators that will be pulling this information, and as you guys saw yesterday, we will ask those questions at the end of each session as time allows, and or ask them at the panel discussion on Friday. I also wanted to just bring everyone's quick attention to the file share pod. It's at the very top right hand of your screen. The evaluation sheet, bios, an updated agenda, and also the presentation slides from today are uploaded. They were uploaded in 2 parts because the file size was too large otherwise to put it into the pod. If you have any issues, again, you can also go to the FTP site and or email me, alicia@urcs.com, if you're having any issues, and I can troubleshoot with you. A couple of quick IT recommendations after lessons learned from yesterday. If you are on a VPN, we highly recommend that you disconnect from it while you're participating in the seminar. The VPN will obviously not allow you to access any of your agency or company data, i.e. your email and things like that, but you should be focused on our seminar anyway, so you don't need that. It will help with your bandwidth, and also a lot of times Adobe itself has a bandwidth. So we're just trying to limit any of the outside reasons why you might be seeing things slower than you should or your audio not as clear. We did have a couple people try this yesterday and it worked really well with their systems. In addition to that, for the audio with Adobe Connect, we recommend that you do use it through Adobe Connect versus the phone number if you can. In order to increase your volume, there is a little caret next to the speaker. If you press on that, you can increase the speaker's volume without needing them to speak louder or quieter. So we do recommend everyone modify their own audio settings to your liking. And then if you are called in through the phone line, please, please, please mute your lines. As we saw yesterday, this particular phone line, because Adobe Connect is technically hosting it, we cannot mute participants. And even though there's a small amount of you on that phone line, we did get some feedback. So please, 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 unless you're a speaker, mute yourself so that we don't have any of that echo or background effect today. With that, that completes our admin announcements, and I will pass it back to you, Jim.
Thanks much, Alicia. Thanks for all the work that you and your team are doing to make this thing run smoothly. Our first presentation is by Katie Goolsby Brown. She's with FEMA Region 4. She's also a member of the task group here, the National Dam Safety Review Board task group that puts on this seminar every year. You know, always contributes greatly to the work. She's going to be talking about FEMA's BCA module. FEMA already does benefit cost analysis as part of the Hazard Mitigation Grant Program, and Katie will be briefing us on that. Katie?
Greetings. My name is Katie Goolsby Brown, and I am a civil engineer with FEMA Region 4 Mitigation Risk Analysis. I'm excited to be here today to provide an introduction to FEMA's Benefit Cost Analysis BCA module. I work as the team lead for the Regional Dam Safety Program and the team lead for the Regional Technical Review Team for Hazard Mitigation Assistance Grants. This includes reviewing benefit cost analysis and instructing the FEMA 2-day training on the benefit cost analysis module. Some of the materials in this presentation are from the 2-day FEMA BCA training. For further information on FEMA's benefit cost analysis module, I recommend to attend the 2-day benefit cost analysis training course. As an overview, today I will be covering an introduction to key concepts behind benefit cost analysis, or BCA, and demonstrate a BCA for a dam rehabilitation project. So let's go into the introduction. So what is benefit cost analysis? Benefit cost analysis, or BCA, is the process of quantifying the advantages or benefits of an action and comparing it to the drawbacks or costs. So weighing the project benefits and the project costs. If an action's benefits are greater than its costs, then it is considered cost effective. Once we add up the benefits for an action, we divide that value by the cost, which gives us the benefit cost ratio, or BCR. Benefits divided by cost equals the benefit cost ratio. If the benefit cost ratio is greater than or equal to 1.0, then the action is cost effective. The purpose of OMB Circular A94 is to promote efficient resource allocation through well-informed decision-making by the federal government. Circular A94 provides guidance on how to perform a benefit cost analysis. FEMA's Benefit Cost Analysis Toolkit was developed in accordance with the guidance in Circular A94 to simplify the benefit cost analysis process. Because benefits are worth more if they are experienced sooner, future benefits must be discounted. The rate at which benefits decline in value each year is the discount rate. Federally funded mitigation projects must use a discount rate of 7%, which is set by the U.S. Office of Management and Budget, or OMB. The FEMA's Benefit Cost Analysis Toolkit already has the discount rate at 7%. That's in the program already. So an example, a mitigation project with $100 in benefits in year 1, with a discount rate of 7%, the annual benefits for year 2 would be $93, year 3 would be $86, year 4 would be $80, and year 5 would be $75. Net present value, or NPV, is the value today of benefits that you will receive in the future minus the value today of costs that you will incur in the future. A positive net present value indicates that something is a good investment. So we're looking at the future benefits in today's dollars minus the cost in today's dollars equals the net present value. So this would include that discount rate. Benefits are any future costs or losses that can be avoided by completion of a mitigation project. So the difference in the cost before mitigation and the cost after mitigation. So when we go back to the earlier equation and look at benefits divided by cost equals the benefit-cost ratio, we can break down further that the benefits equal the cost before mitigation minus the cost after mitigation. Future costs should be counted regardless of who pays for them. Due to the unpredictable nature of hazard events, we estimate the benefit of a hazard mitigation project on an annual basis rather than in specific years. The BCA toolkit uses hazard frequency, damage data, and project effectiveness to estimate annual cost before mitigation and annual cost after mitigation. So we look at the annual benefit equal the annual cost before mitigation minus the annual cost after mitigation. So what are considered benefits? Avoided costs and losses can include physical damage, loss of service and function, injury or death, displacement costs, and emergency management costs. So we'll go through each of these avoided future costs and losses. So avoided physical damage, that's one of the primary benefits of a hazard mitigation project is avoided physical damages. For example, if a dam is rehabilitated to provide additional flood protection downstream, damages to structures or infrastructure downstream would be reduced for flood events up to the level of protection. Also, if a dam is rehabilitated to reduce the probability of catastrophic failure of the dam, this would reduce the probability of damages to the dam and structures or infrastructure downstream. So physical damages can include structural damage to buildings or infrastructure, contents damage, damage to historical or cultural resources, or site contamination. Avoided loss of service and function is another major benefit of hazard mitigation projects. This benefit is only applicable to public facilities, and that it could include utilities, critical facilities such as police, fire, hospitals, and infrastructure such as roads and bridges. For example, a dam rehabilitation project with a roadway on or downstream of the dam would ensure the bridge or roadway remains functional during and after a hazard event. For most public and nonprofit sector buildings, the value of services lost when the building becomes unusable due to a hazard event is calculated by assuming that services are worth what the public pays to provide the services. An example would be a building that provides 911 call services. So we would look at the budget for that building for those critical functions. For critical facilities such as fire, police stations, and hospitals, the value of services is estimated based on the service population and the societal benefits of maintaining that facility in the aftermath of a disaster. For roads and bridges, the value of service is based on the number of one-way trips, additional time and miles required for a detour, the GSA mileage rate, and FEMA standard values. For utilities, the value of service is based on the service population and FEMA standard values. And on the right, we have the service types for utilities and the FEMA standard values. So for electrical power, that would be $174 per person per day. For potable water, that would be $114 per person per day. For wastewater, that would be $58 per person per day. For some hazard mitigation projects, a major benefit is avoided human injury and or death. This benefit is only applicable to some project types, such as tornado safe rooms, hurricane safe rooms, wildfire mitigation projects, seismic retrofit projects, and others such as tsunami, dam failure, or landslide. This is because these project types address hazards that have little or no warning time or protect emergency personnel that must stay behind. An example would be the tornado safe room. In an event of a tornado, the occupant would move from the buildings they're in, such as residential or a school, to the tornado safe room. This would avoid fatalities and casualties to the occupants. On the right, we have the value and the severity of injury. These are FEMA standard values. Injury and death costs come from the value of a statistical life, academic research that was completed for the Department of Homeland Security for death, as well as different levels of injuries. Displacement costs occur when occupants, and that could be of residential, commercial, or public buildings, are displaced to temporary quarters while damage is being repaired. These costs include rent and other monthly costs, such as furniture rental and utilities, and one-time costs such as moving and utility hookup fees. They can also include loss of business income for commercial buildings. Emergency management costs include a range of disaster response and recovery costs that may be incurred by communities during and immediately after a disaster. In many disasters, these costs are much smaller than physical damages or loss of service impacts. These costs can include debris removal and volunteer costs such as sandbagging. Social benefits capture the avoided costs associated with mental stress and anxiety and lost wages that disaster survivors would otherwise experience. These are only applicable to projects that protect residential structures. So only projects that protect residential structures may include social benefits. Projects must have a 0.7 benefit cost ratio before social benefits can be applied. The benefit cost analysis module automatically checks to make sure the benefit cost ratio is 0.75 before applying the social benefits. So that's internal to the program. Now, on the right, we have the social benefit and the value. For mental stress and anxiety, the value is $2,443 per person. Lost productivity is $8,736 per person. Environmental benefits capture the benefits resulting from an improved natural environment. These benefits are applicable to any project type that results in a preserved or improved natural environment, such as acquisition, relocation, and floodplain, stream, or coastal restoration. For declarations prior to September 28, 2020, projects must have a 0.75 benefit cost ratio before an environmental benefits can be applied. This changed for declarations after September 28, 2020. So that's an important date for the environmental benefits. An example of environmental benefits would be an acquisition project where the land use went from developed to green open space. On the right are the type of space and the value. And these are FEMA standard values. For green open space, the value is $8,308 per acre per year. For riparian, it would be $39,545 per acre per year. For wetlands, it would be $6,010 per acre per year. For forest, it would be $554 per acre per year. For marine and estuary, it would be $1,799 per acre per year. So what is not considered a benefit? So anything that is subjective or non-quantifiable cannot be counted as a benefit in FEMA's benefit cost analysis program. Examples would be ease of a project or aesthetic value of a project. Anything not impacted by the proposed project. So there has to be a definitive connection made between the project and the claimed benefits. Additionally, OMB Circular A94 dictates that indirect benefits must not be considered in a benefit cost analysis. Examples would be changes in gross regional economic product, income, or employment, and avoided criminal justice system costs for disaster-related crime. Aggregating multiple projects into one can often increase the overall benefit-cost ratio. Aggregating project benefits does not count as a duplication of benefits as long as the benefits apply to multiple structures or the structure is at risk from multiple hazards. So some examples, we have count 100 properties protected by one drainage improvement as one project. Count both avoided physical damages and avoided loss of function when flood-proofing utilities. Count flood reduction benefits and seismic retrofit benefits for the same structure if the project protects against both hazards. Now, an example would be a fire station in a coastal environment. This also has seismic risk that is retrofitted to seismic risk and wind retrofit. That would be another example in an actual project I saw. So what are considered costs? Costs of a mitigation project include construction costs, any other project-related costs, such as title searches, permits, designs, maintenance costs, any in-kind contribution or match from the recipient or subrecipient. What are not considered costs? Reduced tax base, indirect economic losses, transfer payments. Now, this is per OMB Circular A94. An example would be the insurance premiums, and that would include the flood insurance. Those are considered transfer payments and are not considered costs or benefits for the purpose of benefit cost analysis. Project useful life is the estimated amount of time in years that the mitigation action will be effective. The project useful life is important in the calculation of the benefit cost ratio because it establishes the time frame to calculate the benefits. Higher project useful life values extend the duration over which benefits are calculated, thus raising the final benefit cost ratio. Earlier we discussed the net present value and the annualized benefits. A recurrence interval is how often a hazard event of a specific severity is likely to occur in a particular location. A recurrence interval is often talked about as the X year or Y% annual chance event. An example would be the 100-year flood or the 1% annual chance, meaning that in any given year, there is a 1% chance it will occur. The percent annual chance is calculated by dividing 1 by X. Here, 1 by 100. Projects that mitigate more frequent events are more likely to be cost-effective. Benefits equals cost before mitigation minus cost after mitigation. Project effectiveness measures how well the project will reduce future damages. Structure and acquisition demolition projects are 100% effective. They have zero cost after mitigation. Other project types assume there is still some, but reduced hazard risk upon project completion. This is called the residual risk. An example would be a flood wall protects up to the 0.2% annual chance, the 500-year event. Then it will no longer be effective in events that exceed the 500-year. So we want to look at the cost before mitigation and the cost after mitigation. The term flood control refers to systemic projects designed to reduce flood damage to a facility or area. Examples would be dams, culverts, floodplain and stream restoration, drainage improvements, floodwater diversion and storage, flood walls, levees, and pump stations. BCAs for flood control projects are usually done using the historic damages or the professionally expected damages options, and those are two options inside the benefit cost analysis tool. You will need to past damage data for structures being protected or a professional analysis estimating future damages. Structures can include residential and non-residential buildings, utility infrastructure, and roads and bridges. If your project protects both residential properties and roads, you will need to enter those as separate structures in one project. The BCA toolkit uses the before mitigation damage data to estimate future damages that would be avoided by the mitigation projects. Historical damages to the structure and the year in which these damages occurred. With fewer than 3 events, recurrence intervals must be known for each event. And then professionally expected damages, the recurrence intervals and estimated damages for each event. And for damages after mitigation, the damages after mitigation reflect the level of protection that the mitigation measures provide. So a house elevated to the 100-year flood level, damages will occur once floods exceed that elevation. We'll go into the demonstration. So this is the example. Now, this isn't a real dam. This is an example. So the dam name given is example 01 with an ID of EX0001. The longitude and latitude, because this isn't a real dam, those are just entered in order to get the module to run. For the benefit cost analysis, an address or a latitude longitude is needed. The dam type is earthen. The year constructed is 1928. Dam length is 1,120 feet. Dam height is 35 feet. It is high hazard and unsatisfactory condition, locally owned, with an emergency action plan. We have a qualitative risk matrix. This is showing that the hydro failure mode would occur in the 50-year, is estimated to occur in the 50-year recurrence interval, with damages that would include damages to the dam, damage to the roadway on the dam, damage to 10 downstream buildings, damage to the potable water line downstream of the dam. Now we know that the hazard type is dam levee break based on the scope of work. The project cost is $2.2 million based on a cost estimate. The project useful life is 50 years. And that would be based on FEMA standard values. Maintenance costs are $2,000 per year, and that's an estimate from the dam owner. And the level of protection is the probable maximum precipitation. And that's based on state design requirements for the dam. There are screenshots inside the presentation. I do want to move to Excel file. So this is FEMA's benefit cost calculator version 6.0.0. It is Excel based. It is an add-in inside Excel. And you will see here in my add-ins I have FEMA BCA version 6.0. And that brings up this where I can open the calculator. And here is the benefit cost calculator. Now I can add a project, import a project that someone else has created, export a project that I created, or delete projects. In this benefit cost analysis, we have example 01. And when I look at this, the benefit cost ratio is 1.13, showing that it is cost effective. So let me double click on the example. And there are two structures inside this case study. The first one has a property type of roads and bridges, and the second one would be that water line. Because we know that we have a water line downstream that might be impacted. So let's click first on the first one. Now we put in the project title, and then for this one we put in a latitude and longitude. And once we enter in the latitude and longitude into the benefit cost analysis module, the program will bring up the zip code, the state, and the county. Now property structure type, I've selected roads and bridges because we've been told that roads and bridges will be impacted. In fact, it would be the roadway on top of a dam. If we look at our options, we have residential buildings, non-residential buildings, critical facility buildings, utilities, roads and bridges, and other. Depending on what we select here, we may have different options inside hazard type and mitigation action type. Now, selecting on hazard type, we have quite a few options. Riverine flood, coastal A zone, coastal V zone, coastal unknown flood, hurricane wind, hurricane safe room, tornado safe room, wildfire, drought, landslide, seismic, the dam and levee break we selected, extreme temperatures, infrastructure failure, severe storms, tsunami, volcano, winter storm, and uncategorized. Now remember, depending on what we've selected in this property structure type, we may have different options inside the hazard type. Now mitigation action type will vary depending on what's selected for hazard type. Because we selected dam and levee break, the only option is other. Now we can select historical damages or professionally expected damages. Now we've been told that we have professionally expected damages. For any of these sections, if you scroll on the eye in the upper right corner, it says click to view the help content. For each of these, there is specific help content to that section. When we get to the cost estimation section, that's important for the project useful life. Now I mentioned that the project useful life was 50 years and that was a FEMA standard value. So in order to find those FEMA standard values, we click on the I for the help content and then look at the project useful life. Now this table includes standard values and accessible limits with documentation. Now if I look at major infrastructure for dams and levees, the standard value is 50, which is why I selected that. The initial project cost is $2.2 million. The annual maintenance cost is $2,000. I developed this benefit cost analysis at the end of last year, which is why it's 2020. I could update that to 2021. The year the property was built was given to us as 1928. That was when the dam was built. So we'll go back to presentation for a moment. There's additional information in there. Okay, this is the one I want. So we've been told that the damages before mitigation, per the local transportation department, we have estimated number of one-way traffic trips per day would be 4,000. Additional time per one-way detour trip in minutes is 30. Number of additional miles is 5. Impact is 30 days. We've also been provided additional information. We know that the recurrence interval is 50, and that was based on a report from a professional engineer. Category 1 is set at $3 million, and that's an estimate from the engineer for cost to replace the dam and the roadway on the dam. And then Category 2 is set at $2.5 million, and that's the estimate of damage to 10 downstream buildings. Per the report from the professional engineer, there are no damages estimated after mitigation related to a hydro failure. And that's because the level of protection is the probable maximum precipitation event. So if I go back to the Excel file, you can see that this information has been entered in under professional expected damages before mitigation. We have a 50-year recurrence interval with 30 days of impact. Category 1 was the damage to the dam and the roadway. That was the estimate for those. Now I can change the title. It doesn't have to be Category 1. We can change it to dam and roadway. So that is an editable field. And then Category 2, which is the damages to the downstream 10 downstream buildings, is estimated as $2.5 million. When I look at the benefit cost ratio, it's set at 0.96, which means this action by itself is not cost effective. But we do know that there is a potable water line downstream. So we've included the potable water line as a separate structure. So in the project summary, we've included much of the same information. So it's going to still be example 1 with this latitude, longitude. The project property structure type is now utility. The hazard type remains at dam and levee break. The mitigation action type is other. It's still professionally expected damages. Still a project useful life of 50. Now the initial project cost is set to 1 because all of our project costs were in the first one. So in order for the benefit cost ratio, and since that is a ratio, to analyze, we need to put some cost in there. So we just put a cost of $1 in order for the program to analyze the benefit cost ratio. Now if we go back to the presentation, we've been provided information for our local water department. The type of service is potable water. The number of customers served is 400. The impact days is 30. And the year the potable water line was built is 1980. So that's the information we're going to need. So if we go back to the presentation, to the benefit cost analysis, we have a year analysis of 2020. We can change that to 2021. I just developed this benefit cost analysis late last year. That's when I did this. The year the property was built is 1980. The type of service is potable water. And if I click on that, you can see that I have electrical, potable water, wastewater, or other. The only FEMA standard values would be the electrical, potable water, and wastewater. For other utility types, the value would have to be provided. Number of customers served is 400. We're going to use the default. And using the default has the certain advantages. You don't have to document it. Then the program does the calculations based on the information. Damages before mitigation, we have a recurrence interval of the 50-year event, impact days of 30. Now we could look at the physical damages, but that information was not provided to us. So we enter the information based on the information available. Now the benefit cost ratio is quite high because those project costs are $1. If I close it, we look at the weighted benefit cost ratio from the two structures, and it's 1.13. So the overall benefit cost ratio for this project is cost effective. Now if we had other structures, we could look at adding the mitigation action. If there's a hospital or a fire department downstream that would be impacted, we could delete mitigation actions. If we can't get the documentation, maybe for the water line, we would need to delete that. And we can view the report.
Katie, we've got about 3 minutes left.
Okay. I think I'm almost done anyway, so thank you. Which has a summary of all the information in the project. And we can click home again, and we can see that we could start a new project. If there were another dam or other type of structure we wanted to analyze. So that is FEMA's benefit cost calculator. There are screenshots in the presentation of the module. So you can look at those. And reference that information. Other than that, this is my contact information. There is a BCA helpline that can be contacted 9 to 5 Eastern, Monday through Friday, through this email and this phone number. There is also a website that has information on the benefit cost analysis toolkit, including instructions. And the toolkit itself, you can download that if is allowed by your agency's restrictions. There are pre-calculated benefits for certain project types, and there are certain eligibility requirements. There's a reference guide and the supplement to the BCA reference guide. There's information on training, including the training materials used in the classroom. Some of those training materials were presented to you today. There is also additional information on contacts.
Katie, that answers actually some of the questions that folks have posed. One was, when's the next BCA training module scheduled? I think a couple of people asked that question. Do you know? It sounds like you could get on that website and get the training schedule.
Well, I'm just gonna, did I put that in the right one? Here, let me put it in here. That's the website that I was just on, that benefit cost analysis website. I know there are probably other questions, and I know we're probably out of time. So I will be available on Friday to answer more questions, and I'll be here every day. If you have something.
A couple. Alicia, I'll ask you, can Katie respond to some of these questions in the chat?
Yes, she can.
Mm-hmm. Yeah, so there were a lot of questions, Katie, a lot of really good ones there, too, if you want to take a look at it.
Okay.
One question that, I had, too, it was asked by my good friend Jordan, was the discount rate of, the 7% discount rate. That sounds high. I know for federal projects, I think they're using a discount rate now like 2.5%. And when you get out there beyond year 30, you showed how it drops down, the benefits drop down after 5 years. But if you get out beyond, it's like 1/10 of the annual benefits you get if you do the present value. Do you know the basis of the, why OMB has set it at 7% for this program, for like 4?
It's set by OMB, and that's for the federal mitigation projects, so that may not apply to other types of federal projects. And so that's what's been set by OMB, and we follow that guidance on the discount rate. So unless OMB changes that for federal mitigation projects, then it'll stay at 7%. And that is in the FEMA BCA module. So the FEMA BCA module automatically applies a 7%.
Real good. Well, again, a lot of good questions, about the sort of real technical details about the values, and you might want to take a look at it. One, real quick,
sure,
if we could, the fatality number, $7.5 million for fatality. I think different agencies are around there. Some agencies don't even use a number. Others, like EPA, I think use maybe 8 million a fatality, something around this. Do you know what that's based on?
Yes. So that is the value of statistical life, and that's based on academic research that was completed for the Department of Homeland Security for deaths as well as different levels of injury. So remember, this is what we're trying to avoid. We're trying to avoid fatalities and injuries from the mitigation project. So my example I provided was the tornado safe room. We're looking at occupants moving from a building that is less, it would be more impacted by a tornado to a tornado safe room and become more protected. So we're avoiding
Well, thank you again.
Injuries
You'll see
and
these questions, Katie. Yeah, your presentation certainly generated a lot of interest, a lot of questions.
Okay.
Thank you so much for that presentation. And now I'll like to turn it over to Jason Weiss. Jason, with AECOM, has been working with FEMA and the Dam Safety Program and trying to adapt this to the high hazard potential grant program. So without further ado, let me turn it over to Jason.
Hey, thank you much. Appreciate that. A lot of the information that I'll be covering is also covered by Katie in the previous presentation, but I'll be looking a little more focused on the HHPD program and how it's being applied there, because there is a few differences in how the analysis is completed. So There is a bit, and dam rehabilitation is a little bit different than some of the other typical flood mitigation, so we'll be covering some of the benefits of that. One thing I wanted to touch is I'm going to focus on the benefit cost analysis portion, but I have been working with James Denby from FEMA, who is running the HHPD program, and also Ed Biedenkopf from Atkins, and he's been working on a couple of the aspects, including the probability of failure of the dam. I will cover probability of failure lightly, but Ed's really the person to talk to get more details on that. Okay. Here's just a brief overview of what we're going to talk about today. So I want to start with some of the basics of the program and the benefit cost analysis, and then provide some details on some of the activities that are occurring, and then provide our contact information. Okay. What is the rehabilitation? What is the program actually? The goal is to reduce risk to the nation by improving the safety of dams. It provides assistance for technical planning, design, construction activities. And there also is a funding component of it. While funds were authorized, in 2016 for $445 million over 10 years, that has not been, appropriations haven't kept up with that. In 2019 and 2020, $10 million were allocated for funding appropriated. In 2021, it's going to be $12 million. It is anticipated to go up as the years go on, and it was scheduled to be $60 million for a couple of years, but we don't quite know if that's going to happen or not. And one important, the main component of this program is to reduce the risk to improve the safety of dams, but to reduce the risk to people downstream. So it does not cover things such as lack of deferred operation and maintenance activities. It's so focus more on activities related to structural deficiencies of the dam or inadequate design standards. So those would reduce the safety of the dam as opposed to increase the safety of the dam as opposed to providing more mitigation activities or deferred maintenance. Well, I did mention that the Act does not specifically require a benefit cost analysis. There is a need for one. We want to demonstrate to OMB that federal dollars are being spent efficiently and to help states identify more cost-effective use of awards. Since the awards are limited, hopefully we could provide a way that if states had multiple dams they want to consider, we would hopefully provide a cost-effective way to identify which ones have the biggest benefit to the state as a whole. And they also want to align this with other FEMA grant programs, such as the HMA, that some of the stuff that Katie just covered in the previous presentation. So those do require benefit cost analysis when an application is being done. So, and also to support the application for other FEMA grant programs, such as the BRIC program. Since there is limited funding available through the HHPD, some applicants may have a lot going out to some of the HMA programs, such as BRIC, where benefit cost analysis is required. So, and that may be more appropriate for larger rehab projects as opposed to maybe smaller ones. So it might be better, more effective for maybe a more effective way to get a hold of funds through those other programs. Okay, Katie covered a lot of this information already, but I'll just do a quick recap of what it is. For this case, we're looking at benefit cost analysis basics. Benefit cost analysis evaluates the change in the impacts of an alternative in relation to the before mitigation conditions. And my background is I'm an economist, and we measure the impacts of these different actions. So establishing a baseline condition is very important, and that's the before mitigation condition. And really looking at the estimated damages or consequences both before and after mitigation conditions. So we would look at what would happen before and what would happen afterwards, and really that's the impacts of the mitigation action. Those are what we're monetizing. And really considers the risk of those consequences occurring. And the damages are really the monetized impacts based on appropriate guidance. Different agencies have different guidance for what can be followed, considered a benefit or not a benefit, as Katie covered. And she covered quite a few of the different categories that would be could be realized in a dam rehabilitation project. What is critical here in this one too is how we define the before mitigation conditions. Since this program is designed to improve safety, reduce the risk of the dams, it doesn't take into consideration a lot of the mitigation benefits that are associated with the dam. So dams have a lot of benefits out there, but you don't necessarily take that into consideration for this program because we're looking at a catastrophic failure. So if the dam broke, what would be the damages, the risk of the damages, the probability of occurrence of the dam failure before mitigation and then also after mitigation. Okay, and as was covered previously, there are a lot of benefits of a dam rehabilitation project, and most of these are really cost-avoided benefits as opposed to the benefits of the project. So you might have injury and death, displacement costs avoided, emergency management, costs, and some of the other ones that we've mentioned here. This list is not all inclusive. There are a couple things missing on there, and one of the big ones that would be included is downstream structures and infrastructures. So your residential and non-residential structures and infrastructure such as roads and bridges, or even the cost of replacing the dam back to its current condition is also a cost avoided benefit. For this project, we don't really, a lot of different agencies view benefits of rehabilitation projects differently. So some of them count the benefits that are provided by the dam itself, such as the annualized flood damage reduction benefit would be, if they add all those up, they can justify rehabilitation of the dam. However, because this program is focused on safety issues, it's really looking at the catastrophic failure. So we are looking here at the cost avoided of the impacts of a catastrophic failure. It could also include things such as a loss of a water supply. You might have emergency measures. If the reservoir is used for water supply, you would have emergency actions in order to provide water, municipal industrial water to the citizens. So. Because it's based on a catastrophic failure, you're really looking at the probability of a failure of the dam. And there are a number of challenges when doing the benefit cost analysis, and one of them is obtaining a benefit cost ratio greater than 1. It's pretty difficult in dam rehab studies, partly because you have a low probability of failure for most dams. Many dams have failure rates of 10 to the minus 3 or 10 to the minus 4. Which is 10 to the minus 3 is considered pretty high, but a lot of dams have much lower probability of failure. And you also tend to need high potential consequences. So you might, if there is not much downstream, it's very difficult to justify it. So you typically need a lot of potential structures, infrastructure downstream that could be damaged during a catastrophic failure. And another challenge is stakeholders may have limited information on the dam. Sometimes they, don't know the probability of failure, so that would have to be estimated. Or in this case, most of them should have a breach inundation map to at least identify the population at risk and what could be done. But some of that information may be old or outdated. And estimating the probability of a dam failure is difficult, even with the detailed engineering analysis. We start going to the probability failure modes and looking at the different conditions. How do you come up with one probability failure to cover the whole thing, which you use in the analysis? And the probability of failure can change as the dam continues to age. So what might be a smaller problem now, say a 10 to the minus 3 probability of failure in 20 years because of deteriorating conditions of the dam or other factors, it might be 10 to the minus 2. So that has to be taken into consideration when evaluating this. So when we conducted started working with James and on this program to develop the benefit cost analysis, we wanted to collaborate with a lot of stakeholders in order to make sure that we were able to get the appropriate feedback that could be incorporated into analysis, that we met their needs. So we requested feedback from the National Dam Safety Review Board, and we developed a working group from those, which includes representatives from various state, federal stakeholders. And we have some, can you assist, FEMA and us consultants with identifying issues and reviewing materials. We want to make sure that we had a good understanding of the stakeholders' needs and the perspectives of the dam rehabilitation, and identify methods that can consistently be applied by states, and also to ensure that the process does not cause an undue burden. We've had, over the last 3 or 4 months, we've had monthly meetings with the working group to go over different progress, present pieces of information to them as a further review, and to make sure that we weren't causing undue burden and we met their needs. Through that process, a lot of questions came up from the states, especially about the amount of information that would be required to conduct a benefit cost analysis. As some stakeholders pointed out, it might cost $60,000 to do a full benefit cost analysis when the mitigation measure might only be a couple $100,000. Why should they spend that kind of money doing a benefit cost analysis when the project cost may be very low? And so that was one of the larger issues that some of the stakeholders brought up, is the burden associated with that. So we've been looking at different ways to reduce the burden and make sure that we were able to meet their needs as we go through this process. So we did the benefit cost analysis is kind of broken down into a couple of major components, and one of these is the loss of life considerations. As Katie mentioned previously, loss of life has a statistical value of life of $7.5 million, and it is allowed to be used in a dam rehabilitation project because of the unknown inability for people to maybe get out of the way quick enough. It's a quick flash flood type of situation, so it is allowed to be considered in a dam rehabilitation project. But they didn't really have a standard method that was going to be used within FEMA to estimate the loss of life or the number of people that could be potentially fatalities for this process. So we considered the loss of life, looked at different methods. We reviewed 4 different methods: LifeSim, which is a numerical modeling approach, and HEC-FIA, which uses a simplified LifeSim method. And we also looked at the Wayne-Graham method, which many folks know, and that's based on empirical data from historical dam failures. And then the Bureau of Reclamation consequence estimating methodology, RCEM, is also, which was kind of seen as an update to the Wayne-Graham method. It uses a very similar type of approach, but it's kind of seen as an update. So we took a look at these. The RCEM method is the one that Katie mentioned during her previous presentation, what they use to estimate the loss of life. So we wanted to review these different methods and provided a recommendation on what is considered minimally acceptable, and not acceptable for these different methods. And we have preliminary recommendations, and these have been passed out to that working group with the board, and waiting feedback from those. So we recommended that the RCEM method is a minimum accepted method for inclusion in the benefit cost analysis. The LifeSim and HEC-FIA are also considered acceptable, but they require much more information that might be beyond the abilities of a lot of local stakeholders to undertake those analyses, or could be much more costly to do that. So we want to identify a way that how can we provide basic information that's seen as reliable and consistent. And the RCEM method is kind of seen as an update to the Wayne Graham method, so we selected that as minimally accepted. Our recommendations are currently being reviewed by the National Dam Safety Review Board. And once we come to agreement with them or discussions further, the next step is to present the recommendations to FEMA for policy approval. Then that would be kind of put in writing what is minimally acceptable, so people have a better understanding of guidance and what needs to be done. Okay, the next thing we want to do is provide assistance with completing a benefit cost analysis. And we developed a guidance, a basic primer. And this is to assist with completing a BC under the FEMA Hazard Mitigation Assistance Program. As Katie went through in our previous presentation, there's a lot of steps to it. So we wanted to make sure that when people are considering a dam rehabilitation project under one of these other FEMA programs, they knew what to take a look at and how to do that. So it provides information how to complete a benefit cost analysis for a dam rehabilitation, and it's based on FEMA policy. We wanted to be consistent with the FEMA policy to make sure that it was covered and it could be easily moved into the other HMA program. And in these little papers, it's meant to be, since it's a primer, it's only about 10 pages long. It's not meant to have detailed information conducting the full analysis. It's really meant to provide guidance on what to consider, areas to consider, and then points to FEMA, links to FEMA for some of the other resources. FEMA has a lot of resources available for estimating the impacts of flooding and other issues, so we don't want to recreate that. We just want to point people in the right direction so they can take that into consideration. And it identifies the applicable benefit and cost categories that would be appropriate and provides links to resources. And it also provides information on how to complete a BCA, which is using the FEMA BCA toolkit. As I mentioned previously, the FEMA HMA programs require the toolkit be used for the benefit cost analysis as part of that. And so it walks through how to do that, but it also discusses the limitations of the toolkit and options for overcoming these limitations. While a dam and levee failure is considered one of the hazard types, some of the basic categories you cannot evaluate within the toolkit for that hazard type. For example, downstream residential and non-residential buildings and infrastructure cannot be evaluated directly within the toolkit for this hazard type. As was for like riverine flooding, those are allowed to be evaluated within the tool, but for this hazard category, they're not. So that means that the analysis needs to be done externally and imported into it. And as Katie used in her presentation, they had a professional engineering estimate for that. But some other model would have to be used externally. Either it was developed by the analyst or some other professional tool, and then imported into the toolkit as a other category. So we kind of talk people through that, so if they were going to estimate the damages, they could do that fairly quickly. Okay, FEMA BCA tools and methods. One of the things we also want to do is cover some projects, some tools and methods that could be used within the HHPD program. And one of the things is we've developed is a quick preliminary screening tool. It's an Excel-based spreadsheet, and it's intended to assist with providing an initial analysis of the cost effectiveness of a rehabilitation project, identifying projects likely to pass the FEMA BCA, and prioritizing dam rehabilitation projects within a state. So this is a basic, I wouldn't call it, it takes much less user inputs than would be the FEMA BCA toolkit, so we hope it's easier to use for states and has a little less time burden on their part. But we want it to be consistent, so our approach was to be consistent and complementary to the FEMA BCA toolkit, but not a substitute for it. We wanted to assist with that, but not as a replacement. So you'd still need to use the FEMA BCA toolkit if you do an HMA project. But it uses general assumptions to reduce user inputs. For example, if you don't know the number of residential versus non-residential structures within a floodplain, we use some generalizing assumptions that would kind of distribute the residential, non-residential structures for the analysis. And this reduces user input and lack of limited information. And part of this was we wanted to, as I mentioned, we wanted to make sure that this is something that can be used by states to quickly identify cost effectiveness of the project by using these generalizing assumptions. And if this tool provides a benefit cost analysis greater than 1, hopefully if you wanted them to do a more detailed analysis, that it would also provide a positive benefit cost analysis. But it's also meant for states who have multiple dams and considering which ones they want to apply, do some mitigation measures on. This would hopefully be a quick and easy tool that could be used to identify the benefit cost ratio for these different rehabilitation options and then use that to prioritize their dam rehabilitation within the state. And here's just a couple of screenshots. These are a bit small, but what it is just an Excel-based tool. And you would have different drop-down menus based on the type of impact that would be available, such as the one question there, is there a sediment pool? No or yes. And if you selected yes, it would start asking additional information, it would open up and expand the options. So we tried to keep this fairly straightforward and user-friendly. And here's another one. And what it does come up with is the preliminary benefit cost ratio. One of the parts it does consider here too is the benefit of failure with project and also without project. As I mentioned, it's the difference between the before and after mitigation. So probability of failure is a pretty major component of any dam failure analysis. So getting that part is difficult and hopefully won't be too much of a burden, but I will cover what is happening in the probability of failure analysis in a couple slides. This toolkit is currently it's going to be distributed to the working group shortly for evaluation, and hopefully we'll take some of the feedback from them, their feedback, and revise it. The probability of failure component may also be incorporated in this tool. It's not in there right now, but it hopefully will be at some time in the near future. And to even make it even easier, we're trying to look at other options to show cost effectiveness, and that's one of the major components. How do we show that it's cost effective to do a dam rehabilitation project? For this one, it might be based on loss of life. If you know the loss of life for the dam, it might be as easy as looking at the probability of failure and the potential loss of life from a dam failure and estimating is this cost effective. In this example, if you had a loss of life of potentially 2 people and you had a annual probability of failure 10 to the minus 2, if your rehabilitation project is 1.5 million, it would come above the blue line. So that would show it be cost effective. Something like this might be able to be applied to a subset of the HHPD grant applications in order to minimize benefit cost analysis time and money. So, and one other thing I was going to touch upon with this one is the probability of failure. It does have a big difference here. So in the blue line is a 10 to the minus 2 annual probability of failure, but the red other line is 10 to the minus 3 annual probability of failure. So for example, if you had a loss of life of 2, you can do a rehabilitation project that costs about $2 million, justify it to be about cost effective if it's 10 to the minus 2. But if it's 10 to the minus 3, you really only have about $200,000 project that you can justify for project cost. Anything greater than $200,000 project cost is not going to be cost effective because it's outside of that line. So it does drop very considerably, very quickly. And 10 to the minus 4, it's going to be very, very difficult to justify a dam rehabilitation project if there is that low a probability of failure. So as I said, this could be used as a subset of the potential as maybe low-cost ones for the HHPD programs. That is still being determined and see how this works out. Okay, probability of failure. Ed Biedenkopf, a colleague at Atkins, has been working on this portion. I just wanted to provide what is the current status of the probability of failure in order to give people an understanding. I might not be able to answer a lot of the detailed questions. I'd have to refer you to Ed for those ones, but just wanted to give an overview of what is being considered now and how it may be incorporated into the HHPD program and the overall benefit cost analysis. Since we're looking at a catastrophic failure, the BCA requires a probabilistic estimate of failure. And the HHPD program evaluates risk independently for 3 general failure modes: static, hydrologic, and seismic. It requires states to identify dams to be considered as unacceptable risk to the public. What is defined as unacceptable risk to the public is still being discussed. They had a meeting late yesterday afternoon with the National Dam Safety Review Board in order to discuss that very topic, and discussions are still ongoing. So how do you find that is a little to be determined. It requires risk prioritization for determining grant eligibility. And one of the things that's required here is the probability of failure equals the probability of loading times the likelihood of an adverse response leading to a failure. That will become important over the next couple slides here, really looking at the loading versus adverse response and how those are being discussed at this point. Okay, the probability of loading is showing guidance to estimate the problem for the 3 failure modes. There is some, I see some of the information got cut off on this picture here, but anyways, there's guidance out there that was developed back in 2008, and that's currently being updated to look at the likelihood of an adverse response. So FEMA is modernizing the B713 risk prioritization tool for dams. And really the goal is to provide states a qualitative tool that identifies the likelihood of an adverse response and probability of failure and uses information readily available to the states. Okay, modernization of the P713 is a cooperative effort. Working with the National Dam Safety Review Board work group. And they hope to have an enhanced tool available by pilot tested at least in 2021, and then also plan to release late in 2021 that would allow states to estimate the probability of failure. Descriptors for the likelihood of an adverse response are being developed, and they are developing it from existing guidelines, and it's qualitative, but hopefully that will translate and carry over into a quantitative type of analysis of probability of failure, which is, like I said, is needed for the analysis. And this slide is kind of difficult to read, but it does kind of show that how they want to take a qualitative exercise and correlate that to an annual probability of failure. And here's one more slide on some of the sheets that may be developed. And for example, on this one, that 10 to the minus 2 that's located in one of the cells there, that really identifies the loading associated with the hydrologic event. So at 10 to the minus 2, there is a possibility for erosion at the spillway. So that's a 100-year flood event will engage the spillway, and there could be some erosion. That's the likelihood of the event, of the loading, but then the probability of adverse reaction is the top row there, and that's really, once you get this loading, what is the probability of a failure? So for that one that has a 10 to the minus 2, once it starts eroding the spillway, what is the chances that it will cause a catastrophic failure? In this case, it's 10 to the minus 1, so a 10% chance that once it loads, there will be a catastrophic failure. And that information, the 10 to the minus 2 times 10 to the minus 1, provides your probability of failure of 10 to the minus 3. So you need a 100-year event, and you have from a 100-year event, you have a 10% chance of a catastrophic failure. So these are the type of things that are currently being evaluated in order to identify the probability of failure. The next steps are to refine the preliminary screening tool, the spreadsheet that I showed you earlier, and develop methods to show cost effectiveness. Like I said, we're looking at different methods that could be applied within the program itself in order to show cost effectiveness and a proper use of the money to O&B, and also develop probability of failure methods and tools. And we'll continue to work with the National Dam Safety Review Board work group, and through testing and pilot testing, get their feedback so we can hopefully make this as comprehensive as possible and usable to the state. Okay, and thank you. And I provided the contact information for myself, Jason Weiss, and James Denby. So if there's benefit cost analysis questions, I'm happy to answer those. James would be best for the program itself, and as I mentioned, Ed Biedenkopf is working on the probability of failure. So the three of us have different aspects, but we're going for the same goal of showing cost effectiveness and providing guidance to states. So that's it.
Well, Jason, thank you very much for that presentation. We have a couple of questions here. One of the first ones, and I'm not sure if you're in a position to answer this, but one question was, what is the difference between the High Hazard Potential Dam Grant Program and the Hazard Mitigation Assistance Program, and which is more appropriate for dam safety risk reduction? And I guess you could throw in BRIC in there too. Is that something you think you can field?
Well, I think the other ones, the HMA programs such as BRIC, hazard mitigation assistance, are much more broader based ones. I'll try to answer. James could probably answer far more clearly than I can, but it does. They're much broader based hazard mitigation. So within those, dam and levee failures are kind of one category of the hazard types that are considered. However, for the HHPD program, realizing that there is a lot of dams out there that do need rehabilitation, and so this program is specifically focused on the dam rehabilitation, high hazard potential ones, and to get there is some characteristics in how to identify what is considered a high hazard potential dam. So it must meet those criteria to be considered within the program. So and part of it is to help, since there are so many dams out there, part of it is to help provide guidance to states that would be able to do some rehabilitation and reduce provide safety, reduce the risk to the public. But James might be able to, I don't know if he can get on, but he might have some clear.
I'll help you a bit, Jason. I help you a bit, Jason. Yeah, you were definitely on the right track. So there are different FEMA programs with different requirements, different funding, different times where you can apply for those. So different projects may fall into some of those different categories better than others. So not necessarily one is better than the other. There's just different requirements, different set times, and we're gonna actually provide you some examples of some of those projects. Some of those projects are after their money's given after a disaster. Some are pre-disaster mitigation projects. So there's a whole slew of different types of projects that may be available. We're going to give you some examples of some today, but that's kind of basically, is not one is better than the other. Several different ways to kind of skin the cat and to provide mitigation for dam and levee type of projects.
Thanks. Okay, is there any other questions? Okay, thank you.
Jim Gallagher, did we?
Sorry. Yeah, let me, James, did you have anything you wanted to add to what Preston had to say?
Jim, I'm not sure if James has speaking rights or not right now.
He does. He's just muted. James, if you're trying to speak, you have to hit the green microphone to make your mic hot.
Well, let's see. I can move on to another question, and that is one. You know, it's a common question, I think, for all the presenters. And the question is, failure of a particular dam is a deterministic event based on the physics of the dam and its load. It's not an inherently random event associated with an objective probability of failure. So we assign a probability because of our subjective uncertainty regarding the dam physics, but how do we account for this subjective aspect in risk-informed decision making?
That's a good question, I guess. You know, for the benefit cost analysis, you need some number to put in there. So it is kind of make sure I understand the question correctly.
Yeah, I guess it's not my question, but I have it seems to me the probability on the same dam does change with age. So in New Hampshire, for some state-owned dams, I have state-owned dams that are 200 years old, and I can't imagine that unless they're rehabilitated, that they'll last another 100 years. Honestly, they were designed before, you know, dam safety standards were developed, before knowledge of hydrology and hydraulics. Wouldn't a dam that's that old and has been assessed as in poor condition have a higher probability of failure than, you know, than the universe when you look at the number of failures over the universe of dams?
Yes, it would have a much higher probability of failure, so it does take into consideration conditions and everything, and other factors. So I agree that one that is old and may not meet current design standards, and so it'd be eligible for this type of program. And the condition, this program doesn't cover deferred maintenance, so as long as it's being maintained well, but it could just be design standards and or other issues that are structural issues that are going wrong with the project. Yes, the probability of failure would be much higher for that than, say, a standard dam that has been maintained properly, but also maybe in a different situation, much newer dam that does have better design standards and or, you know, non-structural issues. I guess, does that kind of get the question? I'm just trying to make sure I answer the question here.
I think that gets at it, Jason, to a degree, but it's something I think the other speakers may want to keep in mind in their presentation, you know, because I have seen the same, you know, sort of statistics in all these presentations about the likelihood of failure. There's a question, Jason, on one of your plots, and it was first half of the presentation, so I think it might be difficult for you to answer it without referring to or seeing the chart.
I can back up here.
I think way back, yeah, back. Oh, maybe back. Go a little forward, Jason. I don't know if it's this chart. If you go back a little bit more, Jason, we got a little bit of time. Oh, no, go back. I'll go forward. It was the chart. I see that he's weighing in here, so that was the chart that right here. And the question is, why would a higher probability of failure require a higher project cost to be cost effective for a given loss of life. To be cost effective for a given loss of life. Seems like it should be the other way around.
Well, this one, a higher probability of failure on this one, you could justify, not so much you need to require a higher project cost, but you could justify a higher project cost with a higher probability of failure. So if you had some mitigation actions for that one is 10 to the minus 2 probability of failure, we'll just use that one, and we'll say a loss of life of 2. If you had a rehabilitation project that cost $2 million, it would be considered cost effective for the most part. So you can justify a project that is $2 million or less if you have a loss of life of 2 and a probability of 10 to the minus 2 failure. However, if you get up to a 10 to the minus 3 probability of failure and you have a potential loss of life of 2, you could really only justify a project cost of $200,000 in order to fix it. And that's why, so we're trying, this really shows above and below the line as far as cost effectiveness. And at 10 to the minus 2, you can justify a lot more in rehabilitation project, much bigger rehabilitation project than you could with a 10 to the minus 3 from the benefit cost analysis. That might not have been clear when I did the first presentation, but it's really more how much you can justify. So in that case, if you had 10 to the minus 2 and your project rehabilitation cost was 1.5 million, it would be above the blue line, and that would indicate that it's cost effective and it would be justified. If it costs $2.5 million, it would be below the blue line and would not be cost effective.
Yeah, that cleared it up. Thanks much, Jason. That cleared it up.
Okay, no problem.
I think that is the end of the questions. Jason, you're going to be on the panel?
I can be.
Good. On Friday, that'd be good in case other folks didn't get their questions in.
Okay.
Thank you for that presentation. As a review board member, look forward to looking at that spreadsheet that you showed and do a little sensitivity analysis on some of our dams. So thank you again.
Okay, thank you.
Okay, folks, we're back. Hope you enjoyed your break. Now we're going to be moving into some case studies to apply some of the principles we have heard about over the last day and a half. And our first presentation will be by Danielle Hans from Wheeler & Associates with a benefit case analysis study for the Goose Pasture Tam Dam. And before Danielle gets started, I just do want to highlight, Preston was on here just a second ago about the presentations that are to be evaluated. Preston's been given updated messages in the chat box, the administrative technical chat box about that. I apologize for the confusion with the abbreviations, but Preston will keep you on track. So with that, Danielle, I'm going to turn it over to you. Thanks.
Okay, hi everybody. Thanks for listening into this, and thank you to Katie and Jason for the good overview just before this about the program and everything that goes into the benefit cost analyses. We'll advance the slides. So I'm going to go over just a brief introduction about me, a little BCA overview, but like I said, that was pretty well covered already by Katie and Jason in the previous discussions this morning. Go over a case example on Lower Beaver Brook Dam, as well as Goose Pasture Tarn Dam. These are two benefit cost analyses that have recently been prepared by myself, and just some lessons learned about preparing these benefit cost analyses for these two high hazard dams. So I'm Danielle Hannes with WW Wheeler & Associates, and I'm a professional engineer with about 15 years of experience, and I just really have a general, broad dam safety background. So just experience with risk assessments, hazard classification, flood inundation mapping, as well as some experience with dam design and construction. and experience with PFMs for FERC-regulated dams. So a broad dam safety background is really beneficial, I think, for preparing these benefit cost analyses for dams if you're going to be applying it to that situation. So the two dams that I will be talking about both received FEMA pre-disaster mitigation grants, and I prepared both the applications and the benefit cost analyses for these two high hazard dams in Colorado. So just a little bit of an overview. I can see that the slide, I don't know if it's presenting quite right, but the benefit cost analysis calculator that's available now that was discussed in the prior presentations is Excel-based, and it's based on 6.0 version. My benefit cost analyses that I did in 2017 and 2019 that I'm going to go into were submitted in the previous version of this BCA Toolkit 5.3. It was a different program, not based in Excel, that was used. However, it has the same functionality really for my input in the new 6.0. So for this presentation, I did update those benefit cost analyses so that it was in the new version for everybody to look at. The first case example is Lower Beaver Brook Dam. It's located just west of the Denver metro area in Colorado. And as you can see, there's a map of Colorado on this slide, as well as a blow up of the area. So if you look, golden is kind of on the right side of the map view. And then if you follow Clear Creek all the way up, you'll see where Lower Beaver Brook Dam is and Upper Beaver Brook Dam. You know, a failure of Lower Beaver Brook Dam, it passes right through underneath I-70. So it's located in Clear Creek County, Colorado. It's a small-sized, high-hazard potential dam. It was constructed in 1903, so it's about 120 years old right now. And it's owned by the Lookout Mountain Water District. They're a pretty small district located in Evergreen, Colorado. And the purpose of the reservoir is really to provide water supply, and it's a forebay to the water treatment plant for their operations there. The water treatment plant is really located just downstream of the dam. It's about 100 feet downstream of the dam, so extremely close, and actually would be probably damaged in the case of a failure of Lower Beaver Brook Dam. The picture is just a view of the downstream slope of the dam, the rock fill downstream slope. You can see the spillway on the right abutment in this view, as well as the outlet works. There's an outlet tunnel that goes underneath the dam that houses the outlet work pipe and everything in there. And you can see that kind of on the right abutment of the dam. So it's a concrete-faced rockfill dam. The height is about 39 feet and the crest length is about 224 feet. The upstream slope is 0.7 horizontal to 1 and the downstream slope is 1.25 horizontal to 1. And just if you're not familiar with rockfill dams, a typical rockfill dam these days, constructed to today's standards, is generally about 1.3 horizontal to 1 upstream slope and 1.5 horizontal to 1 downstream slope. So these slopes are quite a bit steeper than what's constructed today. It impounds about 27.9 acre-feet of water, and the spillway is uncontrolled in that right abutment over there. There's a better view on the next slide. It's about 29 foot wide. The pictures in this slide show the spillway at Lower Beaver Brook Dam on the right abutment, and as well as a view of the dam crest. And so there's several sandbags installed on the dam crest, and those are in response to, in 2013, there was some significant flooding in the Front Range of Colorado. Some areas got about 17 inches of rain. It was about a 1,000-year flood event in certain areas. It was a spotty precipitation event. I live on the far west side of Denver, kind of southwest Denver, and we didn't get hardly any rain at all during this event. However, Boulder area and kind of the northwest side of Denver, you know, experienced 17 inches and had some dam failures. Lower Beaver Brook Dam, in this instance in 2013, did not experienced a significant amount of water. The water came up to the dam crest, however, it did not overtop the dam crest, so they were one of the fortunate people in the Denver area that just got a small amount of precipitation in their drainage basin. But it really drew some light on some of the dam safety issues at Lower Beaver Brook Dam. One was how significantly undersized their spillway was. It's only really capable of passing about the 2-year flood before overtopping would start to occur. There's also uncontrolled embankment and foundation seepage. This dam's 120 years old. It's not built to today's standards. There's stability concerns associated with the rockfill embankment, the slopes being much steeper than what's being currently constructed today for a rockfill dam. The age and operability of the outlet works is also of concern. The gate valve is actually about 80 years old and it hasn't been operated in several years. So Lower Beaver Brook Dam, the consequences of failure are two very distinct things. Impacts to the downstream community. So the slide shows the dam failure, the first sheet in the inundation mapping. And the red arrows, just because it's a little bit difficult to see, point out some structures that are within the sunny day inundation zone that would be impacted as a result of a failure of the dam. So as you can see, there are several structures that are just several hundred feet downstream of the dam, and these are houses. It's a high hazard dam, so the loss of human life is really a potential, as well as property damage. There's also impacts to the water consumers. Since Lower Beaver Brook Dam's purpose is really to supply water to several residential taps and businesses and churches, as well as Clear Creek High School, these people would be without water in the case of failure of Lower Beaver Brook Dam. The first thing when I prepared the benefit cost analysis was really looking at what data was available that I could use to put into the benefit cost analysis. So we had hydrology studies to use to develop our feasibility design of alternatives. We also had an estimate of the failure, the recurrence interval that failure was expected, just using that hydrology study and when overtopping and what depths were expected. We also had a hydraulic model that was used for the inundation maps that we could estimate downstream impacts using that. So for this example, for the pre-disaster grant mitigation application, as well as the benefit cost analysis to get the cost, we had to select an alternative for mitigating these dam safety concerns at Lower Beaver Brook Dam. The preferred alternative ended up being a new concrete gravity dam. It was planned to be constructed right downstream of Lower Beaver Brook Dam. The picture in this slide is just a plan view of the dam that was submitted with the application. So it basically has the spillway just downstream of the existing spillway in the same location. It also has an emergency spillway in the middle of the dam, both of those flowing to a combined stilling basin downstream and then down into Lower Beaver Brook. And the dam was designed to an incremental damage analysis was performed, and it was designed to that level of flooding. So there were several other alternatives that were looked at too as part of this, but this was the selected alternative, and the costs associated with that were put into the benefit cost analysis. So the key benefit cost analysis inputs: what recurrence interval is expected, is dam failure expected? So for this example, the 10-year storm overtops the dam by about 0.9 feet. The 25-year storm overtops the dam by about 1.2 feet. Just as a general rule of thumb, most dam safety engineers will use 1 foot over the dam crest as a reasonable assumption to assume failure. That was what I assumed as a failure in this, and I did provide the documentation to support that assumption, just in case if whoever was at FEMA reviewing this wasn't really familiar with something and it is kind of a rule of thumb. I tried to attach as much backup as I could just to justify my assumptions. So I assumed a failure at 25 years for this. However, given the condition of the dam and just, really the condition of the dam and that it was 120 years old, I probably could have justified using a smaller flood, but that really wasn't needed once I got further into the benefit cost analysis for this structure. So the new concrete dam was assumed to withstand a 1,000-year event, and that was based on the incremental damage analysis that was performed. The cost of the mitigation alternative that was put into the benefit cost analysis software was $5.3 million, and then we went on to estimate the benefits. So the benefits of this project include reducing the risk associated with the loss of human life. It's still a high hazard dam, so there is still a risk of that, but it's significantly reduced with the new dam. Damage to the downstream residences and businesses is greater than 15 structures that are impacted by this. Damage to the water treatment plant. Damage to downstream roads, water infrastructure, and they're not able to provide water to 14 government sites. Also in Colorado, drought protection is really a big thing, and if Lower Beaver Brook Dam were to fail, the district would not have that storage available for their water consumers to protect against drought. They also would not be able to provide water to residential water customers. And that was really the only benefit that I quantified in this benefit cost analysis. I did provide a memo that went over all of these other benefits of the project that weren't quantified within the benefit cost analysis software. However, in the benefit cost analysis software, the only thing that was accounted for was this residential water consumer water loss. So how I went about quantifying this value for the number of customers that were without water and for how long they would be without water, I looked at how many customers were without water by, there's 480 residential taps, and the census data for Clear Creek County had a population, a number of 2.54 people per household. So that came up with 1,219 people would be without water. And then I had to estimate how many days the customers would be without water. So there are several alternatives to mitigate this situation. One would be rebuilding the dam, but that would just take a very long time. The quickest thing that we thought would be appropriate is, building an upstream diversion on Beaver Brook that could supply the water treatment plant with water. So the first thing we would do was just do an engineering design of the diversion structure and the pipeline. So that would include a site visit, a survey, engineering flow calculations, construction drawings, specifications, and also preparing applications for agency review. We estimated that to be 28 days. Regulatory review and approval of the design. So the Army Corps of Engineers would need to review this. We assumed a nationwide permit would be needed. That has a review time of 45 days. Clear Creek County would need to be notified, and we would need to file an application with them, as well as the Colorado Department of Health and Environment, since modifications were being made to the drinking water supply. We assumed 45 days for this regulatory review period just because that's the review period associated with the nationwide maintenance permit. We did not assume any time for if regulatory agencies came back with comments or things, so we were rather conservative in this assumption. We assumed that the contractor would be selected concurrently with the regulatory review, and that construction of the diversion facility, pipeline, and water treatment facility intake would be about 35 days. This would include mobilization, access to the diversion site, material purchase, installation of the diversion and pipeline, And so that was a total of 108 days to go from engineering design all the way through construction. It's very optimistic in the assumptions, just to not try to overestimate the benefits associated with this project. So things that this timeline did not account for were damages to the water treatment plant that might occur. It's located within 100 feet of the downstream toe, and it's possible that that could happen. Also, downstream water mains are located within the inundation zone that are likely to be damaged, and those damages weren't accounted for in this timeline. So this is a little bit small, but it's a view of the benefit cost calculator. Katie went into this in a lot more detail, but I want to focus on the bottom part of this slide, if you can see that. So I used a project useful life of 50 years, and that's the FEMA standard value for dams. And I tried to use FEMA standard values as much as possible just to avoid having to do documentation that really wasn't needed to get the benefit cost analysis above 1. And then also in this slide is the input of the project cost. So it's 5.3 million was entered into this slide. And then for the maintenance cost, 0 was input for the annual maintenance, and that was just justified by the maintenance associated with the new dam was just expected to be much less than the maintenance that's currently paid for by the Lookout Mountain Water District with the 120-year-old dam that has some rather significant issues. This is just a slide kind of showing the input of the potable water loss. So up at the top, the number of water customers served, 1,219, as well as $105 a day, which is the FEMA standard value for water loss function. And then in the tables below, it just shows prior to mitigation. At a 25-year recurrence interval, I'm expecting 108 days for that those people to be without water. And then below, it shows that I'm not expecting any water service losses after the new concrete dam is built. So in summary, the benefit to cost analysis really shows that the benefits were 7.6 million associated with just 100 days for 1,219 people to be without water. And the costs of the project were 5.3 million. So that renders a benefit cost ratio of 1.44 million. The award for this project was $4 million. The district, the Lookout Mountain Water District, is paying for 25% match. So that would be about 1.3 million that they are covering for this project. The next example case study that I'm going to talk about is Goose Pasture Tarn Dam. It's located in Summit County, Colorado, so it's a little bit further west of Lower Beaver Brook. Just if you, in the slide on the side, you can see the Denver metro area and the location of Breckenridge within Colorado. It's a Colorado ski town, so if any of you have ever been here skiing, I'm sure you're familiar with Breckenridge. The slide below shows Goose Pasture Tarn Dam at the bottom of the slide. It really flows through an inundation. A dam failure would affect the town of Breckenridge and flow into Lake Dillon just downstream, so you can see that. It's a large-sized high-hazard dam. It was constructed in 1965. It's owned by the town of Breckenridge. Really, this is their only raw water supply for the entire town. So just a plan view of Goose Pasture Tarn Dam. You can see the reservoir. It has 2 spillways, a service spillway and an emergency spillway that goes over the embankment. and both discharge into the Blue River and then flow down into the town of Breckenridge. There's several downstream residents too that are just right near the Blue River and right near the dam. You can see one on the aerial image that's pointed out, as well as you can see the Tarn treatment plant that's located just downstream of Goose Pasture Tarn. At the time the FEMA application was submitted, this was the only water treatment plant that Breckenridge had to serve their customers. It is located higher up and further out of the floodplain, so I'm not sure it would be damaged. However, if the forebay to it, the Goose Pasture Tarn Reservoir, isn't there, it wouldn't really be able to serve customers in the case of a failure. So a little bit about Goose Tarn Dam. It's a zoned embankment dam. The dam height's about 57 feet. The crest length is 550 feet. It impounds about 812 acre-feet of water, 400 of which is contracted to Vail Resort. And right now, just because of the condition of the dam and the situation that's going on there, it's restricted by about 244 acre-feet. So that only leaves about 167 acre-feet of raw water storage for the town of Breckenridge currently. So the most significant dam safety issue that's going on at this structure is there's continuous voids underneath the reinforced concrete of the service spillway. So the schematic on this slide shows the water that's basically infiltrating the embankment and causing groundwater pressure to push up against the bottom of the spillway slab. It's a pretty significant concern, hence why the dam has been restricted. There's also other concerns associated with this dam, including the potential for internal erosion along the outlet conduit or through the embankment. As an interim dam safety measure, the emergency spillway at the dam was actually lowered by 4 feet in order to have it serve as the primary spillway during this situation until a permanent solution could be implemented at Goose Pasture Tarn. So the spillway on the right is the RCC emergency spillway. That was lowered and it's now functioning as the service spillway temporarily. And then the spillway on the left, the service spillway, there's several sandbags installed in the crest of the service spillway to prevent it from operating. These temporary dam safety repairs can accommodate about the 100-year flood discharge. This is just a plan view of the modifications that are planned at Goose Pasture Tarn. So the planned modifications are just to replace the 2 existing service spillway and emergency spillway with one single robust spillway. Also, the installation of filter diaphragms around the outlet conduit, an outlet pipe liner, and a downstream chimney and tow drain within the embankment. These mitigating efforts will really address the identified dam safety issues. So the consequences of failure associated with Goose Pasture Tarn Dam include impacts to the downstream community as well as impacts to water consumers. Same as Lower Beaver Brook. It serves the water consumers and there's also people located downstream. So this is just a view of the 100-year storm in conjunction with the failure of Goose Pasture Tarn. And I'll go on to the next slide. This is the next sheet in the inundation map. You can see the devastating impacts that it would have to the downstream community. There's several critical facilities located within the floodplain, including police stations, town halls, fire stations, as well as Highway 9. Highway 9 is a main access road, and it's a huge transportation route for this area. It's significantly impacted by a failure of Goose Pasture Tarn Dam. The first thing I looked at preparing the benefit cost analysis was what data was available. Fortunately for this, when I started preparing the benefit cost analysis, we were about 70% done with the design package. So I had an alternatives analysis report, hydrology that was complete, project costs to a 90% design level, as well as a screening level risk assessment workshop documentation, really to identify the potential failure modes and their likelihood of occurrence. And we also had the inundation maps, the model available from those to use to estimate the downstream consequences. So what reoccurrence interval was expected associated with a dam failure? And for the existing dam, we assumed a 100-year storm. However, there's several PFMs that were identified to occur during a normal situation that had a very high likelihood. These included concentrated leakage that occurs through the embankment along structures and structure contacts beneath the service spillway slab and beneath the RCC emergency spillway, internal erosion along the outlet conduit, and a structural failure of the service spillway slab. So all of those had a high likelihood just during a normal situation. So we probably could have used less than a 100-year storm and been justified doing so. We didn't need it for the benefit cost analysis, so we just kept it pretty conservative. The new spillway was assumed to fail at the 100,000-year storm, and that's based on a probable maximum flood. Costs of the mitigation alternative were about $19.5 million. Benefits with this project included reducing the risk associated with, one, the loss of human life. There's several lives that would be expected to be lost just with the devastating inundation through the main section of the town of Breckenridge. Damage to critical infrastructure, including fire stations, justice centers, police stations. The town hall is located within the inundation. Healthcare facilities, child care centers, wastewater treatment plants, all of those things would be impacted by a failure of this dam. There's over 2,000 properties that are impacted by a failure of Goose Tarn Dam, as well as damage to streets and road crossings, loss of potable water to critical facilities, schools, government sites, loss of sanitary sewer services, loss of potable water services that means no fire protection for certain people, traffic impacts associated with Highway 9, loss of potable water service for residential water consumers, as well as property impacts that were significantly impacted by this dam failure situation. So the last three are the only benefits that I really quantified within the benefit cost analysis tool, because these rendered a benefit cost analysis that was greater than 1. And I will point out that this one was layered a little bit more. The 3 were input in there, but even if you removed one of them, it still had a benefit cost ratio above 1. And that was just to provide a little conservatism with the review by FEMA. So Goose Pasture Tarn Dam results in significant impacts to Highway 9, and it actually overtops 13 road crossings by about 3.6 feet to 8.5 feet with flood depths and velocities of about 12 to 22 feet per second. So if the first 3 crossings downstream of Goose Pasture Tarn, one is of Highway 9 and a couple are of a smaller route, actually there's no direct connection between the town of Blue River and the town of Breckenridge, so it removes that. The only detour that's really available that's open year-round is about 132 miles to get from one side of the town of Blue River to Breckenridge. And it takes about 2 hours and 38 minutes, and that's in the summer. So the average annual daily traffic for Highway 9 is about 8,000. And the repair time was estimated, if a situation were to occur in this, was about 78 days. And this was based on the 2013 flooding, like I mentioned prior. There was a stretch of highway that was significantly damaged by that rainfall situation from Lyons to Raymond. And that's how long it took Colorado to get the temporary repairs for that stretch of highway to make it passable for residents. We assumed that this would take a similar amount of time. It was about the same length of road. Goose Pasture Tarn, the length of road that would need to be repaired was about 10 miles. The Colorado Highway 7 was about 14 miles. But the situation at Goose Tarn had a lot more road crossings and things like that over the Blue River. So we thought it was applicable to use for comparison. So just to show you the input that was put into the program, the average annual daily traffic was input as the number of trips per day. The detour additional length in time and miles was input, as long as the federal rate that was just a FEMA standard value. So under the reoccurrence interval tables, prior to mitigation occurring, these impacts were expected to occur for 78 days at 101-year interval, recurrence interval. And then after mitigation, these effects, or these impacts to the traffic weren't expected to occur. The other thing that was accounted for was just potable water impacts. The water consumers, there's about 10,649 people that consume water within Breckenridge. This includes the resident population as well as the non-transient population, which is defined as people that it's kind of a Colorado ski town, so population that's there over half the year but might not be there as a resident. So that was divided by 2. So that's 11,218 people divided by 2. And that came up with the number of water customers that was included in the benefit cost analysis. The amount of time that they were assumed to be without water was 78 days, which is the same as the traffic impact. In reality, this would probably be a little bit longer because once they were able to get access to the locations to repair some of these mains that would be damaged by the flood inundation depths and velocities, getting lead parts and things, it would take a little bit more time. But that was our assumption, was it would be the same amount of time. This is just to show you how it was input into the benefit cost analysis software. So the number of customers served is input at the top, as well as the value of the water service, which is just a FEMA standard value. And then the before mitigation, number of days customers were assumed to be without water was 78 days at 101 recurrence interval. And then after mitigation, these impacts are not expected. We also looked at impacts to 161 houses that were expected to be flooded with very high depths and velocities. We used a FEMA standard value of $110 per square foot used in the benefit. This is a ski community, and the property values are quite high, so this was really conservative to not overstate the benefits. This was actually added in a reanalysis of the benefits just to account for any potential cost increases that might occur with construction, especially in today's construction age. So just in summary, the dam repairs for this were estimated to be $19.5 million based on the 90% design. And the potable water loss, the benefits associated with that were about $11.9 million. And that in itself accounted for a benefit cost ratio of 0.61. Traffic impacts associated with Highway 9 accounts for benefits of $13.2 million, which is about a benefit cost ratio of 0.68. So those two alone got above the benefit cost ratio of 1. The property impacts added in of the 161 of the highest flooded properties was a benefit of about $7.8 million, and further increased the benefit cost ratio to 1.7. So the award for this project was $10 million. They got a resilient infrastructure grant, and the remaining costs are going to be covered by the town of Breckenridge, the $9.5 million-ish. So some basic information that's needed for benefit cost analyses for a dam. This was covered pretty well previously, but it's just, you need the cost of the project. You really need a good handle on the recurrence interval of failure pre and post project construction, as well as the knowledge and quantification of the project benefits. Inundation maps can be very helpful. General knowledge of the reservoir water use is also very helpful to understand what sort of impacts would be associated with a failure. Some of my lessons learned in preparing these couple benefit cost analyses, they can be a little bit challenging just because your clients, if for some reason they're not selected to get the grant, they've spent this money on this FEMA application as well as this benefit cost analysis, they can be quite pricey, and they really don't get a lot out of it if they're not selected, if they're stronger applications than yours. So I try to be pretty cost effective in doing these just because you don't know what's going to happen. And so for all of them, I started pretty simple. I tried to just use estimated information to see what benefits were the most fruitful. And then once I kind of determined what benefits, could be easily documented and provided, a high benefit cost ratio, I spent more time developing the background and, putting a lot more thought and consideration into those benefits than, using some of the other benefits that might only get you a 0.2 benefit cost analysis, and then I'd have to go back and use get some more information. If possible, I always try to use the FEMA standard values just to avoid documentation. They're not going to be questioned because that's their standard value that FEMA accepts. If possible, I recommend including extra benefits into the application. That way, if somebody is reviewing your application and may or may not agree with some of the things that you've assumed or professionally estimated, you have a little bit of cushion that will allow your application still to go through and have your benefit cost analysis still above 1 if something's modified. Make the analysis as defensible as possible. Also, think outside the box. Try to find benefits that may be defensible without a lot of work, just to save time and effort. So those are just a few of my takeaways. Again, that's me. If anybody has any questions, I plan to participate on Friday too, and I think we have a couple minutes too if anybody has any questions.
Danielle, that was an excellent presentation. And we do have a couple of questions. I'm going to ask mine first, though, because this is an issue when FEMA's trying to consider how we apply this to the high hazard dam grant program, where there's not a lot of money available. And I appreciate your concern about your clients spending upfront money and perhaps not getting a grant. Could you give a sense of the level of effort to go through one of these BCA analysis and perhaps the cost?
Yeah, sure. It is kind of tied to how much information you have going into it. Like, for example, Goose Pasture Tarn Dam, we had 90% design. We were working on the 90% design. We had a lot more information. And that one, I spent about $25,000 on, that was consulting fees, keep in mind, but that included both the grant application as well as the benefit cost analysis. Those weren't separated out. Beaver Brook, it was a little bit more because I had to develop the whole alternatives analysis as part of that application. That was about $45,000. And it was my first one. I really hadn't done a benefit cost analysis prior to that, so that probably resulted in some additional fees.
Thank you for that information. The talking about the Lower Beaver Brook project, I think it applies to the goose one, goose pasture one as well. Was FEMA involved in developing the preferred alternative? You did the alternatives analysis in both, and it sounded like they didn't have any involvement in identifying the preferred alternative. But is that the case?
They reviewed it after the application was selected, but we went through and we tried to look at it the same way that FEMA would look at it from a NEPA perspective, going into it with the application, so that hopefully, but they did relook at it. Both cases, they agreed with our assumption on the preferred alternative.
Another question we have is, the benefit cost analysis is justified for one probable failure mode, but the project actually addressed several probable failure modes. Is there any way to communicate that in the benefit cost analysis?
So I tried to keep the benefit cost analysis really simple, just because of the level of effort that goes into doing it. But I also included a memorandum that documented all of my assumptions, and in that memorandum I documented, all the additional things that wasn't accounted for in the BCA tool, however, that the project really, mitigated for, and, just a lot of additional things that weren't specifically quantified in the BCA.
And this is a specific question, again, I think about Lower Beaver Brook Dam. I think you said you got like $7.6 million for potable water credit today. I think the total damages was $13.6 million, and the question is, how did you get to 7.6 from the 13.6 million?
So 7.6 was the benefits, and the cost was 5.3, and that's the calculation based on the benefit cost analysis software. So this is, on this slide, this is what came out of the program.
Probably the 7% interest rate to compute the present value, sounds like.
Yeah. So so there's some internal calculations that go into the program as well.
I think the last one we have time for is what was the federal funding request versus the amount awarded?
In both cases, it was we requested for Goose Pasture Tarn, we requested $10 million. That was the maximum we could have requested based on the program, and it was received. And Lower Beaver Brook, it was, a 75% FEMA and a 25% match by the district, and that's what was requested, and that's what was received.
So there's a couple of questions that I didn't get a chance to ask, but you may want to look at the Q&A and get back with those folks. I appreciate that. But thank you very much. That's a great presentation, great application of what we just been hearing about. So nice job, Danielle.
Thank you.
Next up, we've got Rachel Bisnet from Stantec, and she'll be talking about a risk-informed decision-making for an extreme consequence dam in Australia. Rachel?
Hey, thank you. Can you hear me all right?
I can hear you fine. Absolutely.
Okay, great. So thanks for that introduction. So what I wanted to talk about today is benefit cost analysis and just risk-informed decision-making in general for an extreme consequence dam project that I've worked on in Australia. The client did give us permission to present on it, but asked that we withhold some key information, so I'll be as specific as I can be. A brief introduction on myself. I'm a geotechnical engineer at Stantec. I've worked on a number of large dam, hydro, and navigation locks, design and construction projects. But over the last few years, I've really spent a lot more time focusing on risk assessments for dam safety and dam improvement projects. So here's a brief agenda of what I'd like to cover today. And during this presentation, one of my goals is to convey to you how risk assessments can complement standards-based assessments. Risk-informed decision-making can be used to reduce uncertainties and refine risk assessments, and how cost-benefit analysis is a tool for evaluating a LARP, or as low as reasonably practicable, in dam improvements, and also justifying the business case for those improvements. So just a quick overview of risk assessment in the context of this project. This was performed, the project is located in the state of Victoria in Australia. So as part of their regulations, they require dam owners to consider risk within their dam safety management program. They essentially roll up under the overall ANCOL umbrella. And so this concept of understanding risk to loss of life is really intertwined in how they manage their dam portfolios. I won't read all of this to you, but it's basically describing that. As we heard in yesterday's keynote, there are a few different levels of risk analysis. The PFMA and SQRAs are definitely more common here in the U.S. This project utilized the quantitative risk assessment, which is the typical standard for Australian projects. In a quantitative assessment, we're calculating annual probability of failure at multiple reservoir levels, multiple seismic event levels, and assigning appropriate consequences from dam break modeling that's been performed for multiple reservoir levels. And then we prepare a cumulative risk plot. So we're thinking in terms of cumulative risk, not just individual failure mode risk. So a QRA follows the same structure that we're familiar with. It starts with a PFMA, and that's where we're going to identify the hazards such as hydrologic or seismic events. And then we identify the failure modes that are applicable to that particular dam. And then the probability of failure and consequences are estimated, and then cumulative risk is estimated. So when we go through probability of failure estimates in a quantitative risk assessment, we're doing nodal estimates on our event trees, and then basically calculating a conditional probability of failure given that event tree. Cumulative risk at the end for this risk estimation part is a big F in the FN curve. So just a brief overview of the project. The reservoir, as I mentioned, is located in Victoria. It's a couple hours outside of Melbourne. The project was built between 1948 and 1952, and it consists of two embankments. The main embankment is on the right in this image, and the subsidiary embankment is on the left. The purpose of the reservoir is for water supply, and it's been classified as extreme consequence because there's a significant population center not too far downstream.
You'll note on looking at this photo, this aerial, that there is no spillway. Instead, the primary control for drawdown of the reservoir is through the low-level outlet works that are below the main embankment. And you can see kind of the small house at the downstream toe and then the intake tower within the reservoir. The main embankment is about 42 meters high. It's a homogeneous lean clay embankment with upstream and downstream rockfill zones. There's a gravel transition zone material between the clay and the rockfill. It's pretty short, it's pretty thin. It's about 2 feet on the vertical. And along the embankment foundation contact, there's a short concrete cutoff wall that was constructed just upstream of centerline. That concrete cutoff wall detail is a pretty typical feature for dams of this era. The downstream slope is about 2 1/4 to 1 along the earth fill portions. The subsidiary embankment is 21 meters high. This dam was constructed first during construction of the project, and they had some kind of selected higher plasticity clay material in the barrow that was used to form a central clay core. And the more abundant lean clay that we saw on the main embankment was used for the remaining fill here. There are thin rockfill shells with that same transition zone on the upstream and downstream slopes. Originally, rockfill was only placed along the bottom portion of the downstream slope. You can see, a little bit hard to see, but on the detail, just from the bottom bench on down to the toe. The portion above the bench was added post-construction. And a key thing to note from this figure is the downstream slope is 2 to 1. So fairly steep for this type of embankment. So at the beginning of the QRA, we performed a review of historical records, and there were 2 reports that were especially beneficial. One of them was called the Water Commissioner's Report Concerning Water Supply, and this was prepared by the chief engineer of the project. It identified kind of his thoughts and considerations throughout the design phase, throughout the geotech investigations, and then during construction as well. So it gave some really incredible insight into what the designers, what the contractors were thinking, what they were paying attention to in the field. Really, really valuable information as you're sort of ingesting how to evaluate nodal probabilities in a risk assessment. The second report was on the geology of the proposed dam. This was prepared by a state geologist to summarize the overall setting at the site, the borrow materials that were available. They paid some particular attention to what were termed deep lead deposits in the left abutment of the main dam. So this was kind of a former mining site. There were a couple of mining relic tunnels still at the site at the time of when the dam was being considered. So the geologist gave some recommendations to consider realignment of the dam or other treatments of those mine works. A few other kind of summary of key information that was obtained from the records is shown here. A lot of this is sort of foreshadowing where we got to in the initial risk assessment. So through that review of the records, we learned that the main embankment reef fill, which is just their term for the lean clay that was used, was compacted relatively dry of optimum in pretty thick lifts and with generally a greater compactive effort than was used in the subsidiary embankment. The main embankment conduit, so that low-level outlet works, was excavated in rock. They did take care to put high plasticity clay on top of the conduit as part of the backfilling operations and around the cutoff wall where it crossed the conduit. They did extend the clay blanket across the upstream side of the left abutment to cover those those known mining relics. The subsidiary embankment had a 2-year construction stoppage that occurred near the top of the core. They basically hop skipped over to the main embankment, built that up, and then came back and finished off the subsidiary. A little bit after construction, some slips started to appear on the downstream slope of the subsidiary embankment. They ended up extending the rock-filled zone closer to the crest, remember above that bench. Later on, 6 to 9 inches of settlement along the entire upstream slope was observed, so the dam was giving some signs of distress a little bit. As part of investigations for that, a standpipe was installed kind of around the midpoint of the dam, which the records indicated found that the phreatic surface was near the top of the core, so very close to that construction cutoff zone. And we actually discovered that standpipe and went searching through the records for it because there was as we were walking around the site, an old pipe sticking out of the top of the dam, and nobody knew what it was. We dropped the pebble down in it, and the water was still pretty high. So we went a dig in the records to specifically find that. Again, as part of the QRA, we also performed a site visit. This overall project did include a comprehensive dam safety inspection that was performed earlier in the project by a couple other folks on our team. So this visit was really just for the purpose of becoming familiar with the site and having an in-person look at potential failure modes and just kind of better understanding how the site conditions could play into what we've seen in the records and kind of our growing understanding of what the PFMs could be. The first observation that we made is, I'm just going to run through a few key observations we saw. So over on the left abutment of the main embankment where those mining relics were, there was always seepage noted in the left groin on the downstream side. That location, when we kind of overlaid it on some geologic maps, was at the approximate location of the deep lead contact with the top of bedrock. So indicated that maybe there's some seepage within that material within the abutment. And then there was always historical runoff down the left groin and just the potential that that was sort of exacerbating issues. Furthermore, there was a known abandoned mining shaft located kind of just upslope of that seep location. The next observation was in the outlet works tunnel. So this is a dry tunnel with kind of an interior pipe that actually carries the water. As we started walking through the tunnel, began to notice some grout ports that appeared to have been abandoned. So you can see a close-up of one of those on the right. And also some pretty significant concrete repairs that had been performed primarily in the crown of the tunnel. The grout was visible in a few defects within the concrete, and it appeared to be sort of a polyurethane kind of expansive foam type of grout. That grouting was not noted in any of the records, and so just kind of something that we saw as we were on site. The next key observation is, this nice green grass right at the toe of the main embankment. Talking with the operator, he's reported that there's always been nice green grass there. They, over time, have sort of attempted to install superficial French drains to help control the sogginess there, but that kind of nice green grass area remains, which sort of indicates that maybe we're getting a little bit of seepage along the top of ground. And then the final observation is, this is a little bit skewed, but the seep was not in the middle of subsidiary embankment. It's
located over on the left groin of the subsidiary embankment. And elevation-wise, it corresponded with the construction cutoff layer. And so the operator did report that any time the reservoir was filled above that rough elevation, that seep would appear. When they kept the reservoir below it, there was no seepage. So, you know, the story was starting to come together a little bit, and we're able to kind of begin painting a picture. There's one significant data gap, and that was associated with the subsurface geology within the left abutment of the main embankment. So we knew of those deep lead deposits. There wasn't a whole lot of information on them. We didn't have a ton of detail on, you know, for example, whether it would be filter compatible with the main embankment fills, and just sort of how that interface would look and respond. So that uncertainty became a pretty important item to consider as we move forward with the risk assessment. So given the data review, given some simple analytical assessment, so, you know, rerunning geotech stability and seepage models, that sort of thing, we were able to develop the initial risk profile. And this is a plot of just the main embankment. The orange line is the cumulative risk, and then the blue dots are associated with the individual potential failure modes. We had a nomenclature to label them, so we sort of knew what we were looking at, but many of these are related to flood loading conditions, and then overtopping, internal erosion, stability failure modes. So what's important to note here, we do compare the results to a limited tolerability. ANCOLD right now uses the diagonal line up to 100 fatalities, and then sort of straight lines it across beyond there. There is a proposal on the table for this to kind of imminently be extrapolated to this diagonal. So many of the owners there have been working against the full diagonal as they consider upgrades for the last few years. So main embankment plots entirely above the limit of tolerability. Given the uncertainty we had based on the records and some of those field observations, we performed a pretty grossly simplified uncertainty evaluation where we simply defined reasonable upper and lower bounds for certain input parameters. One of these was the warning time used in the consequence calculation. One of them was the rate of erosion for the embankment fills in the internal erosion calculations. And the goal of this was just to kind of have a big picture understanding of the potential impact that the uncertainties could have on the results, and try to make a decision on whether it was worth digging into those uncertainties to refine the risk assessment before moving into upgrade considerations, or just moving straight ahead and dealing with it as part of considering mitigation measures. So what you'll see on this slide is the orange line, the one on the right, is the upper bound of FN curve, and then the blue one on the left is the lower bound. Neither of them drop below the limit of tolerability, and there is a pretty significant, almost 2 orders of magnitude or more difference between those lines. So what that said to us and to the client is that the uncertainty could have a significant impact on the magnitude of risk reduction that may be required. And the last thing they would want to do is go forward with an upgrade project and then come to find out when it gets reassessed afterward that, oh, they're still maybe hovering right around the line because we didn't bring it down far enough dealing with those uncertainties. So This is the main embankment. The same exercise happened for the subsidiary embankment. Stability here was the real driver with that 2-to-1 downstream slope of the that subsidiary embankment. Again, repeated uncertainty exercise, found some similar conclusions. You'll notice here that the fatality, the potential loss of life value for the subsidiary is significantly lower than for the main embankment, and that's just simply due to the higher foundation elevation, so the kind of lower volume of potential release. So the decision was made to move forward to an uncertainty reduction phase of the project, and in consideration of that, we developed a targeted geotechnical field and laboratory investigation program, and we designed it to reduce the uncertainty and try to fill some of the data gaps that we had. So outlined on the next few slides are just some of those key issues we had in the initial risk assessment, what the uncertainty or data gap was, how the investigation plan would deal with it, and then what we anticipated the outcome to be as it would impact a revision to the risk assessment. So the first issue was the stability of the main embankment. Again, that downstream slope was 2 1/4 to 1, which ended up giving us kind of marginal factors of safety under normal reservoir levels. So as it was, that embankment stability risk was screened out of the initial assessment because we did have at least a factor of safety of 1.5, but it was basically just 1.5. So wanting to just make sure that that wouldn't be an issue in the future, we decided to collect some undisturbed samples to perform some additional strength testing, and more importantly, perform it at appropriate stress ranges, given what the potential stability failure surfaces were. Also, as part of this, installed some additional piezometers in the embankment and the foundation to get a better handle on the phreatic surface, and then ran some hydraulic conductivity tests as well. For the subsidiary embankment stability, that ended up resulting in a high probability of failure due to low factors of safety for stability. So here we had very much the same goals as for the main embankment, but obviously it was much more important to collect these samples and try to nail that down. Time to failure is a parameter that affected all the internal erosion initiating mechanisms. So the information we had available indicated that the embankment material as well as the foundation infill, so any gouge material within the joints within the bedrock were indicated to be potentially dispersive just based on some Emerson class tests. Following some recommendations within the piping toolbox document, which is pretty commonly used as the basis for internal erosion risk assessments in Australia, we elected to perform whole erosion tests, which are kind of targeted towards more directly estimating the erodibility of embankment fills or foundation materials. So we performed those tests. That gave us the possibility to modify the original assessment of probability of initiation for erosion and time to progression of any internal erosion failure modes, as well as the breach development time of progression. So had an impact at multiple nodes on the event tree. Cracking near the crest. This one sort of became an issue simply because an investigation hadn't been done to go look for it. So the piping toolbox kind of gives the guidance that if you don't go look for it, you need to
generally assume that it may be there. In particular, the benches within the abutment, so the left abutment of the main embankment primarily, had the potential, just due to the slope and configuration, to cause differential settlements within the embankment. And then just kind of a general potential for desiccation cracking along the crest that could be an issue at flood stages. So by digging a few test trenches within the crest, that gave confidence in the assessment of those initiating mechanisms. And then the last one was the filter compatibility of the transition zone material. So, we had a few particle size gradations from the construction records and assessed that this very clearly was not a perfect filter, but it seemed like it would give us some filtering between the embankment and material and the rock fill. So performed a few test pits, evaluated particle size distributions of that transition zone material, and then used that to update the filter compatibility calcs just to have a better, more confident understanding of how reliable that material would be as a filter. So again, that would end up impacting many of the internal erosion initiating mechanisms. So went through the field and lab program, analyzed all the data, and given that evaluation, put together a final risk assessment. What's on this slide are the cumulative probability of failure curves for the main embankment and the subsidiary embankment together. So the main embankment is this lower orange curve that has the higher number of fatalities on the x-axis. And then the subsidiary embankment is the blue curve that ends up stepping up along the limit of tolerability. I've also highlighted with a couple different individual markers certain key failure modes. So this would be the little f. And what those indicated is that sunny day events, so with the reservoir at normal pool, were the primary driver for risk. And this kind of came down to how the owner was operating the reservoir at the time. For the subsidiary embankment, stability far and away was the risk driver, and that's what we see up here. For the main embankment, it was internal erosion, and that's kind of what's setting our peak on the FN plot for the main embankment here. Combining those into a single curve for the reservoir, because risk comes from the pool that's impounded, not necessarily the dam itself. So when we think about risk in this context, we want to bring it all together and think about risk due to the reservoir. Here's a single curve that accounts for how the two separate embankments were, with those same failure modes plotted just for reference. So when we move into considering risk reduction, we know we have to deal with this part up here that crosses the limit of tolerability. That's, according to the regulations, mandatory risk reduction has to be done. And then everything below the limit of tolerability, we have to prove that we're satisfying the principles of ALARP. Thinking about that information in a little bit different way, we prioritized the potential failure modes, the different internal erosion initiating mechanisms based on their contribution to the total risk profile. So this essentially gives us now a prioritized list as we think about risk mitigation measures of how we're going to get the most bang for our buck from a benefit cost standpoint. So by and large, if we deal with stability of the subsidiary embankment, that's going to get us the most gain in terms of reducing our risk profile.
So moving on to the next phase of the project, this is where the risk reduction options come into play. Just kind of big picture for reference, the process that was followed, which, this can vary a little bit from project to project, but I'd say generally is pretty similar across the board. The first step is you want to identify measures that are going to deal with the failure modes you've identified as being critical. So each of those measures may address one or more of the potential failure modes, just kind of depending on what those PFMs are or what the initiating mechanisms are. In this case, we formulated risk reduction options. So those were combinations of different measures that we took through the overall evaluation process. Given those risk reduction options, we assessed residual risk. And so that's how much risk reduction has been achieved versus the baseline from our final risk assessment I just talked about. And then answering the question of, have we gotten ourselves below that limit of tolerability? And then finally, once we get below the limit of tolerability, we have to think about ALARP. So as part of ALARP, we prepare concept designs, conceptual cost estimates, and then evaluate the risk reduction options using the principles of ALARP. So considerations for risk reduction options. The idea is to kind of go on both ends of the spectrum to start with. So considering a standards-based upgrade, that might be the most you could do. And the thing to think about there is what features is the dam missing that would be included in a new dam if we were to design it today. So on this dam, a 100% no erosion filter along the downstream slope, a filter diaphragm where the conduit daylights. Those are the types of features that we would expect in a new dam that this one can't quite check all the boxes for. Went through what the kind of grossly estimated cost of basically that new dam type of construction would be, and the cost was essentially untenable and not would have impacted the owner's ability to continue providing their essential water utility service. So we also then thought about whether operationally they could make some modifications to achieve acceptable factors of safety. This may be better stated as acceptable risk. So for example, can they tolerate a permanently lower pool from a water supply standpoint, and using the forecasting that they developed, that was indicated to not be an acceptable option. Other things you could think about here that weren't necessarily appropriate for us, but sort of the other bookend on this is you could potentially decommission the dam. That would take away the risk, but that just, again, may not be realistic from the owner's point of view or the kind of societal impact point of view. So if you get through the standards-based options and they're determined to be untenable, then it's appropriate to move forward with a risk-informed approach. As David mentioned yesterday, risk reduction options can be either structural or non-structural. So what that means is we have the opportunity to potentially make improvements to things like warning time, which can reduce the PLL value, so move us further to the left on the x-axis, or we can add upgrades, modifications physically to the dam, and that tends to help bring us down on the y-axis on the probability of failure. So always keep in mind you can pull both of those levers and see where you can make movements. So for this project, we outlined 6 risk reduction options, and those are presented here grouped on the left side by potential failure mode. So basically starting with stability of the subsidiary embankment and then adding on the next most prevalent risk for, according to that prioritized list I presented, for each of the different risk reduction options. So when we think about it by measure, what that means is to deal with stability, we proposed a rock fill buttress that would be constructed on the downstream slope of the subsidiary embankment. To deal with internal erosion issues near the crest of the main embankment, the thought there was a filter trench that could be constructed from the crest. To deal with internal erosion issues near the crest of both embankments, extend that filter trench all the way across to the subsidiary as well. To help deal with that construction stoppage zone, stoppage elevation in the subsidiary embankment, adding on to that a partial downstream filter. Thinking about, I'm on number 5 now, the possibility of a poorly compacted zone in the main embankment, just given that the compaction criteria changed as they moved over to that dam. The idea that was put forward was adding a Swedish berm. Just given the geometry of that embankment, the geometry of the internal zoning, kind of removing that rock fill cone, replacing it wasn't really a viable option, so a Swedish berm would be just adding on to the downstream. And then number 6, IM13 is a seismic-induced internal erosion mechanism, and so for that one it would be adding an earth fill buttress on the main embankment with a full height filter. So a really, really significant dam safety modification in that case. So given all of the risk reduction options, we move forward into calculating residual risk. And so the baseline residual risk comes out of the final risk assessment. And for the reservoir overall, it was about 1.7 times 10 to the minus 2. This is basically a total loss of life. And so each risk reduction option, the residual risk for that option was calculated assuming that the potential failure mode being treated was going to be treated fully for that option. So that contribution to risk from that potential failure mode sort of falls out of the total risk. And then the benefit is simply the reduction in total loss of life when you compare that risk reduction option to the baseline value. We can plot that information on FN curves, and this gives us an idea of at what point do we first step below the tolerable risk limit. So you'll see risk reduction option 1, it doesn't quite, it sort of follows this line and doesn't quite get below the line, so that in and of itself would not be an acceptable option. And we kind of move down the list until we get to the first one that does drop below the line. So that's kind of the first step in evaluating whether or not these are acceptable. Then once we get below the line, now we start to think about ALARP. And there's 4 principles of ALARP. The first one is cost effectiveness, and so that's measured by cost to save a statistical life and proportionality. And these are kind of similar to the cost benefit concepts that we're talking about today. Good practice is the second one. And so that's simply asking, is the proposed upgrade in line with the state of the practice? Does it address any known dam safety deficiencies? You know, are you basically handling the basic issues that are known about? The third one is the existing level of risk. So here's where we consider uncertainties, how close the baseline is to the limit of tolerability. You know, is there justification to maybe go more than an order of magnitude below the limit of tolerability, just so we have comfort that we're not going to approach that limit if uncertainties shake out a little bit different than what we had hoped. And then finally, societal concerns is the fourth one. And that's where we need to comment on the consequences of failure, proximity to population at risk, how critical the infrastructure is. Is society going to be impacted adversely during construction or as a result of construction? So taking a deeper dive into the cost-benefit aspect, as I mentioned, that gets evaluated according to cost to save a statistical life, which is the first line on this table, and then the proportionality factor is the second line. Cost to save a statistical life is kind of a long equation, but it considers the annualized cost of implementing the risk reduction measures, the annual existing expected value of the risk cost, which is basically the failure probability times the monetary losses to the owner for the existing dam. It considers the annual expected value of the risk cost post-risk reduction, so what is the cost of the residual risk that would still be there. It considers the annualized expected value of life loss for the existing dam, the annual expected value of life loss post-risk reduction, any existing annual operating costs, and then post-risk annual operating costs. The second line is the proportionality factor, and that's a ratio of the cost to save a statistical life against the present value of the project. And so AMCOLD provides some guidance and for evaluating both CSSL as well as the proportionality factor. Basically where we ended up is you'll notice risk reduction option 1 has fallen off. That didn't get below the limit of tolerability, so it doesn't get evaluated as part of this ALARP consideration. Given the parameters provided by AMCOLD, anything less than $5 million per life has very strong justification for the upgrade. So that applies to numbers 2 and 3. In that $5 to $10 million, $5 to $20 million range, there's strong justification for the upgrade. So that's number 4. 20 to 100 million, we're now getting into the moderate justification, and then anything above 100 million, there's really poor justification. So that's applicable to number 6.
I'm sorry, Rachel, we've got just 2 more minutes.
Yep, thank you. So in terms of proportionality, this is, our kind of understanding of where it falls in terms of acceptable levels of risk below the limit of tolerability. So anything around 10, you would be justified in using that proportionality factor to make improvements when risks are just below that limit. Your kind of threshold proportionality factor becomes 3 for risks that are just above the broadly acceptable level. So it's really describing kind of what the threshold value we would consider here is. Thinking about cost benefit in a slightly different way, we can plot the reduction in potential loss of life, which is the top line, and this is in terms of orders of magnitude, compared to the baseline, alongside the annualized cost of implementing the risk reduction option. What this shows us is that we sort of hit a sweet spot around risk reduction option 4, where the benefits, so the reduction in PLL flatline, but the costs keep increasing. So this just graphically is a really nice visual, intuitive way to understand where you might be at that sweet spot. Cost benefit isn't everything for ALARPs. We also have to think about the other factors. Good practice, in this case, RRO4 would address that known construction defect in the subsidiary embankment, so we kind of tick the box there. Given the existing level of risk, risk reduction option 4 is approximately 1 order of magnitude or more below ANCOL's proposed limit. So it gives us a little bit of a buffer on uncertainties. And then in terms of societal concerns, there's a potential temporary increased risk to water security due to a possible drawdown during construction. So just closing here, a few key takeaways. The historical records are really important for the data they can provide, as well as just understanding the standard of care that was used. It's really important to document the negative when you're describing why potential failure modes weren't evaluated. The risk profile should feel right. Does it pass the gut check? We knew stability was an issue, and that by far was the risk driver. So does it just make sense? Having an understanding of the risk drivers gives us insight into uncertainty and risk reduction opportunities. And then finally, being able to explain ALARP considerations is really, really critical for justifying the selected alternative. In this regulatory context, it's more than just explaining cost benefit. It's kind of bringing that full kind of comprehensive picture to demonstrate that you're suitably below the limit of tolerability. So that's all that I have.
Thank you. We really run out of time, but there is a couple of questions. I know one was about your benefit cost analysis. The question got asked before you got into that last part of your presentation where you went into detail about the benefit cost analysis that you did to support the risk reduction actions proposal. So I think you've answered that in your presentation. And another question I have is, let me just read it. It appears with residual risk option 1 that you are relying entirely on the FN plot rather than using the FN as a tool to help make decisions. Being that close to the tolerable risk line, it seems like judgment could be used to justify that as a viable alternative. Can you comment on this?
Yeah, so I think what that comes down to is justifying the other factors for cost benefit. So with option 1, it does fall right on that line, still a little bit above it. By letter of the law, that's not okay. So, if that were to be accepted, we would need to be very, very, very confident in the uncertainties that we had and figure out how we can dial them in to inch below it at least. The other really important piece of this is the regulations do require that ALARP is met. And so it's not just a matter of saying, okay, we got below the line, we're good. It's a matter of saying, have we done enough? And that's why these other concepts in terms of cost to save the statistical life, proportionality factor, as well as just the commentary on best practice and the other ALARP considerations are really critical to make it a more well-rounded decision making rather than just a pure cost benefit or limit of tolerability, yes, no, binary answer.
Great. Rachel, excellent presentation. Thank you so much. There are a couple of other questions that I didn't get to, and if you want to take a look at the Q&A, perhaps respond to the questioners, that'd be great. Our next presenter is Jules Malama from the Bureau of Reclamation. Jules is also on the task group that puts together this seminar every year, represents the Bureau on that. We appreciate that. So, Jules, let me turn it over to you.
Thank you, Jim. Can you see my screen?
I can.
All right.
Yes.
Thank you. Thank you very much. I'll get started. So Jim mentioned, my name is Jules Malama. I'm with the Bureau of Reclamation. I'm a program manager in the Dam Safety Office, overseeing dam safety activities for the Upper Colorado Basin region. I'm privileged to speak to you at this annual technical seminar where we've had so many great presentations already, and there's plenty more to come. I'm glad to be presenting at this time because all the acronyms and definitions have already been defined by Katie and several other people and Rachel, so I won't have to go through that. So thank you very much for those. I'm here to talk about reclamation's dam safety cost-effective analysis approach on modification projects. So for my outline, I'm going to be talking, like I mentioned, about the dam safety program, just a very brief description, talk to guiding documents that we related to managing our portfolio, plan selection for modification projects that we have, the required analysis into these plan selections for the alternatives, cost effectiveness, and then talk to alternative costs that go into the plans for comparison. And then at the end, I'll give a couple examples of the example arrays that we include in our modification reports. As I look through my outline here, this presentation can be a couple of days. So bear with me as I try to just kind of touch on the main things as we go forward here. So just a brief description with reclamation, specifically the dam safety program. Our mission is to ensure that reclamation facilities do not present unreasonable risks to the public safety, property, and all the environment. Reclamation manages 487 dams and dikes, 360 of which are high those that would cause life loss or significant damages if they fail. They are the dams managed within the dam safety program. Primary use of reclamation, the water that's stored within reclamation facilities is for irrigation and hydroelectric power generation. And then we also have ancillary benefits such as recreation, flood control, industrial and municipal water, and wildlife enhancements. So reclamation operates under, the Dam Safety Office operates under the Dam Safety Act. It authorizes the Secretary of Interior to construct, restore, operate, maintain new or modified features at existing dams for safety of dams purposes, including modifications. 15% of the cost for modifications allocated to authorized purposes of the structure. These costs are reimbursable over 50 years, in which the work undertaken is essentially complete.
Hey Joel, sorry to bother you. Some people are saying they're having a hard time hearing you. Would you mind speaking up a little bit?
Okay, let me try and make sure I just pull my microphone to my mouth. Does that sound a little bit better?
It says that your audio is fading in and out at some time. So just make sure you're staying nice and close to it.
Okay.
Yeah, I think you got it, Joel's with it. Yeah, adjusting your microphone. I think that was it. Thank you.
Okay. All right, I'll try and hold on to it so I can be close. I think I was talking about annual costs converted to present worth values over the remaining economic life of the dam by use of the discount rate prescribed in the principles and guidelines, which changes from year to year. For example, for 2021, the discount rate that reclamation is using is 2.5%. And I know Katie talked to the 7% discount rate. Our reclamation, we're using 2.5%. The Secretary of the Interior has been authorized to approve modification expenditures less than $20 million, meaning that we don't have to go through the process of mod reports to get Secretary given authority to allow.
Hey Joel, we keep losing you. I'm not sure. Can you maybe try calling in through the phone line? It seems as though your audio might not be working properly.
Let me do that. See, is the number close by where I can see it?
Yeah, it's in the notes section, but I can also put it in the chat for you to see.
If you don't mind doing that. Let me try a different earpiece here. Just give me 1 second before I switch to the online. Can you hear me at all?
At the moment, yes. I'm just worried about the issue of it fading in and out.
Let's give it a try, Joel.
This is Alicia, but yes, we can hear you a lot louder.
Annie, can you hear me now? Okay, we'll try using that. Okay, I muted my Adobe Connect, so hopefully that won't provide feedback. All right, so let me get to the next slide here. Okay, so reclamation uses several federal guidelines, including the ones shown here. You got the principles and requirements for federal investments in water resources. These principles were in the past limited in application to 4 agencies. Corps of Engineers, Bureau of Reclamation, TVA, and Natural Resource Conservation. In order to increase consistency and comparability in decision-making across the federal government, the application of these principles and supporting documents has been expanded to include other relevant projects, programs, and activities, including Homeland Security and therefore FEMA. Just to keep in mind, the principles and guidelines encompass several documents. The next document that we use in reclamation is a DOI agency-specific procedures handbook. And here it lists the federal objective, which is intended that the federal investments in water resources as a whole should strive to maximize public benefits with appropriate consideration of the costs. Public benefits encompass environmental, economic, and social goals. The third book that I've got here on the screen is the Reclamation Handbook for Economic Analysis of Dam Safety and Modifications. So basically, Reclamation has taken information from the federal guidelines and created a book that's specific to Reclamation's dam safety activities. The federal objective as outlined in Public Law 110-114 specifies that federal water resources investments shall reflect national priorities, encourage economic development, and protect the environment. So basically, sustainable economic development looking into related to unwise use of floodplains and protecting and restoring the functions of natural systems and mitigating any unavoidable damage to natural resources. So if we're doing a modification and we anticipate we're going to do some damage, we need to mitigate those things. Some of the guiding principles for federal investments include healthy and resilient ecosystems. Federal investments should protect and restore the functions of ecosystems and mitigate any unavoidable damage to the natural systems. Should encourage sustainable economic development. Floodplains being critical components of watersheds. And then public safety. Threats to people, including both loss of life and injury from natural events should be assessed in the determination of existing and future conditions. Ultimately, in the decision-making process, alternative solutions, which include structural and non-structural elements, must avoid, reduce, and mitigate risks to the extent practicable and include measures to manage and communicate residual risks. The impact and reliability of alternatives on these threats must be evaluated and shared with the public and decision makers. So basically, as we're going through the process, we do public meetings where we get the input of the public and provide information to decision makers. We need to provide environmental justice. So this is the fair treatment and meaningful involvement of all people regardless of race, color, national origin, or income with respect to development and implementation and enforcement of environmental laws, regulations, and policies. And then the last one here is watershed approach. The watershed approach to analysis and decision-making facilitates evaluation of a more complete range of potential solutions and is more likely to identify the best means to achieve multiple goals over the entire watershed. So here, I'm going to talk a little bit about the general requirements. There are a lot of requirements, and I'll talk through a number of them, but we'll focus more on the design of alternative and plan selection here and throughout the rest of the presentation. So as listed here, some of them include the evaluation framework, base available science, and commensurate level of detail. Collaboration. Federal agencies should collaborate fully on water resource-related activities with other affected federal agencies and with tribal, regional, state, local, and non-governmental entities, as well as community groups to realize more comprehensive problem resolution and better informed decision-making. We've been talking a lot about risk and uncertainty. The guidelines include that in our general requirements, risk and uncertainty. When analyzing potential investments in water resources, areas of risk and uncertainty should be identified, described, and considered. Knowledge of risk and uncertainty and the degree of reliability of the estimated effects will better inform decision making. And some of these areas that we need to include are climate change, future land use. And when it comes to design of alternatives, we talk about alternative plans. Strategies or actions are to be formulated in a systematic manner to ensure that a range of reasonable alternatives are evaluated, all the way from feasibility and taken into final design. The guidelines require that each alternative plan is formulated to consider the following 4 criteria, which is completeness, effectiveness, efficiency, and acceptability. The final array of alternatives, and I'll show examples of 3 recent modification projects at the end of this presentation. It includes the plans and strategies or actions. In alternative plans, strategies, actions that can effectively address a problem through the use of non-structural approaches if they exist, and must fully be considered and carried forward to the final array of solutions. And such solutions must be given full and equal consideration. as an alternative plan, strategy or action that is preferred by local interests with oversight or implementation responsibilities must be included in the final analysis. In our situation, we have water users, so basically if they have a certain alternative that they want to consider, we are to take it through at feasibility level and we'll carry forward that idea that the water users are interested in and analyze it to find a design for consideration by the decision makers. And then these last two kind of sort of related, the environmentally preferred alternative, which where required by the National Environmental Policy and Act, must be included in the final analysis. And then the mitigation of unavoidable adverse effects associated with each plan or strategy. Then there's also the requirement of transparency in decision making, and which is helped a lot by presenting these ideas in a document that can be presented with the MOD report and provides that transparency that is required. So I thought to present the process that we go through in a graphical manner. I'm kind of just walking through the steps. Like I said, this has an input. The inputs into these things can be talked about over a day or a couple of days, but I just kind of wanted to kind of be very brief, and specifically the rest of the presentation will concentrate more on the cost effectiveness analyses. But as we talk about the inputs, starting with the need. So you first have to identify the need for the modification. Is it something like you have an active seepage that you're trying to fix? Or is there a defect that you've realized? Or did you identify high risks from a potential failure mode analysis or from a comprehensive review of the facility or technical response team looking at an incident? Once you get that information, you go through an issue evaluation process. And then eventually, if you find that you do have an issue to be evaluated, you send it forward to the feasibility analysis process. With this, you include investigations, so field investigation, data collection. With your analysis, you provide input from consultant review boards. All in all, considering what your assumptions are, and then at this point, at the feasibility level, you come up with the cost estimates for construction and construction oversight that will be presented in the array of alternatives. So continuing this graphic in the next slide here. So things that go into the array of alternatives include the non-structural alternatives that I've mentioned before. The array should have things that are of public benefit, structural alternatives that are presented to fix the issue that you've identified, local interest alternatives. Then the capital costs, you come up with those estimates. And then if there are things that you've identified that need to be mitigated, so you mitigate those unavoidable adverse effects. From that, then you present this information for decision making. And the decision, which is discussed further in the guidelines, is required to meet the Dam Safety Act, is technically feasible, and is cost effective, as we're talking about. And then we have to take into account the environmentally preferred alternative. Once a decision is made and the alternative selected, then that alternative can be taken into final design. There are financial thresholds for analysis included in the cost effectiveness analysis. For dam safety activities for Bureau of Reclamation projects, we have three categories determined by dollar amount based on the present value. Greater than $20 million, we do a standard analysis. Between 10 and 20, it's a scaled analysis. Less than 10 is excluded. And then there's also other exemptions based on the project or activity, and looking at, is the project or activity below the threshold, investment thresholds? Is it involve only routine maintenance and repairs? Does it involve emergency actions? If it's not a water resource investment, and the extent to which an equivalent pathway already exists. We're talking about general guides to required analysis, as outlined in the guidelines. So the analysis should include information to justify the use of any particular analytical method that you're using. So why is the method used? How does it compare to other methods? What are the risks and uncertainties inherent with that particular method? And the options for analysis outlined include the benefit cost analysis, regional impact analysis, cost effectiveness analysis, break-even analysis. For my presentation, as I mentioned, I'm going to focus on the cost effectiveness analysis that reclamation performs. As we've had presenters today presented on cost benefit analysis, I hope that has been beneficial for the audience to understand a little bit more about those aspects. So cost effectiveness. This is a method that seeks to identify the least cost way to achieve a given objective. A reclamation cost effectiveness is determined by comparing the developed sum of the costs and lost benefits that is generated by the project over the period of analysis of each alternative. A cost-effective plan is one that, for a given level of output, there is no other plan that costs less. However, we don't always select the least cost alternative. We consider ALARP, just as Rachel mentioned in the BCA. We also, in cost effectiveness, we will look at ALARP. For some projects, we'll select to add a small cost to take care of the next highest potential failure mode. And I'll give an example in one of the projects that we have done that. Then we also consider unquantifiable benefits. So these are things that you can't really put a cost to, but they include social benefits, public perception, and so on. So when is cost effectiveness used? According to the guidelines, cost effectiveness analysis should be used when a level of service is mandated, and thus the objective of the analysis is to determine which program or alternative under consideration achieves the mandated level at the lowest cost. For example, for dam safety projects, and it actually mentions those. When a level of service is mandated for dam safety projects, we want to reduce the total risk at a facility to an acceptable level, guided by the public protection guidelines. However, the limitation of a cost-effective analysis is that the analysis may not provide the necessary information to determine if the project or alternative provides the net economic benefits. I'm going to touch very briefly on the difference between cost effectiveness and cost benefit analysis. The objective of BCA is to evaluate the estimated economic benefits and the cost of an action and its effects on society and compare the two. In theory, a BCA is supposed to take into account all quantitative and qualitative benefits and costs that accrue to society. However, in practice, and I think as we've heard previously, due in part to lack of information or technical limitations, it's rarely possible to quantify all of the costs and benefits. The results of the BCA are discounted to the net present value using the discount rate that Katie mentioned. If net present value is positive, the project is economically justified. The way I look at it, with cost effectiveness, you have to do something. Which alternative is the most cost-effective alternative? Once selected, that's the one that you proceed with. With benefit cost analysis, with the proposed solution, you look at the net present value for the benefits and the costs and determine if the project is justified. If it's not justified, you cannot proceed until you find a solution that will have a cost-benefit ratio greater than 1. In most instances, a certain amount over 1. So what are the public benefits included? When we talk about lost benefits, what are some examples of those? Federal investments in water resources as a whole should maximize public benefits with appropriate consideration of costs. That's what the guidelines say. So public benefits encompass environmental, economic, social goals, including monetary and non-monetary effects, and should allow for the consideration of both quantified and unquantified measures. In this presentation, I'm going to focus more on just the environmental and economic benefits as we talk through how we come up with some of these. So in talking about environmental, so what are the NEPA considerations? So there's a long list here, and some including, alternatives. Are there alternatives that can reduce environmental impacts that you should consider? Water quality. The lower the reservoir during construction of one alternative, the lower the water quality downstream can be, which can impact fish and recreation, so you may consider doing something different in that case. Cultural resources. How would the alternative impact these? Public meetings. Input from the public. We may, in our offices, designing things, look at something, but not necessarily understand what the public
if
really
you're
uses
on the phone, please remember to mute yourself. Your audio is coming through.
Listening into public input will help us determine which alternative is the best to reduce unforeseen impacts. And if we do find that some of these impacts, for instance, if closing the dam, the road across the dam is going to impact how people move around
Mr. Bay?
in the winter.
Hello?
Sorry, I think I hear somebody speaking in my ear. So talking about an example we have is a project that with going forward, we were going to have to close the road across the dam for a number of months, and therefore would impact how communities moved across, and so we're going to have to provide some mitigation for that. Economic benefit analysis. And Jim, I'm looking at my time. I think it stopped. Is this the right? I have 5 minutes left. I'll assume that's the correct time, so I'll keep going. Economic benefits. Economic benefits are used to estimate the value of the benefits, so the lost benefits. As we go through the cost effectiveness analysis, we'll look at, as I mentioned, more of the lost benefit costs. Economic analysis uses the conceptual with analysis, meaning benefits with the project in place, or without analysis, which is benefits without the project. And then you compare the two and see the difference. Benefits of improved structure, we typically estimate the lost benefits if the dam was not repaired and either failed or is removed. So talking about no restrictions, full irrigation, recreation benefits are provided, reduced monitoring. And then the cost of dam safety action, so the cost of the actual design and construction costs, future operation and maintenance, NEPA and cultural impacts mitigation as a result of the repair activities. All the while keeping our mission in mind to ensure that reclamation facilities do not present unreasonable risks to the public safety, property, and or the environment. Some of the economic benefits include those listed here, such as I mentioned before, agricultural irrigation, M&I supply, water supply, power generation, recreation, and fish and wildlife. So what are how are some of these benefits estimated? So for irrigation benefits, we look at net farm income lost with or without failure. And we use farm budgets, historical USDA state level prices, crop prices, cropping patterns, expenses. Recreation benefits, you look at the value of the recreation visit multiplied by the average visitation to the site. M&I, again, you look at the water supply multiplied by the amount of M&I that is used. And the hydropower, similarly, the value of the generation, power generation multiplied by the amount of generation supplied. And then I mentioned the alternative costs. So the cost to come up with the alternatives, basically, and this is typically done at feasibility level. So you have the design costs all the way from feasibility, and then you estimate the the cost for final design, construction costs, construction oversight, estimation of mitigation and unavoidable effects, road repairs that will be needed, and then the cost of lost benefits, and then interest during construction. In accordance with the Water Supply Act of 1958, to capture the opportunity cost of the federal funds that are expended during the construction period, interest is charged on all federal funds expended during the construction period, interest during construction. The opportunity costs are calculated as the interest revenue the federal funds could otherwise have generated over the construction period. For 2021, this is 2.5. So I'll go quickly through a couple of examples here that show the arrays. So here the needful action was to address the identified public risks at Project 1, which is related to the 3 potential failure modes associated with the internal erosion. So we had internal erosion along the outlet works conduits, through the embankments, and through the foundations of the Dike A and Dike B. The preferred alternative in this case was the lowest cost. Note that we always present the non-structural alternatives, reservoir restriction and dam breach, as required in the guidelines. Example number 2 for this project, the dam had undergone detailed and extensive investigations that were initiated by Reclamation under its dam safety program. And the need for corrective action was primarily to address PFM number 1, which was internal erosion at the Zone 1 and right abutment bedrock contact. However, corrective measures will also address PFM 4, which was internal erosion through an earthquake-induced upstream right abutment slide. The preferred alternative is not, as I mentioned, is not always the lowest cost alternative. In this instance, the alternative preferred was extending the existing outlet works conduit upstream. This is an example of that completeness of the analysis as required by the guidelines. Not only do we address the main potential failure mode, but we also take care of the residual potential failure modes that are the next highest contributors. And again, it was a difference of about $5 million compared to the lowest cost that we looked at. In doing this, we look at the overall risk at the facility to as low as practicable. Just a couple more slides here. For this last example, the need for corrective action at this dam was based on the inability of the present dam and dike embankments to accommodate rare flood events, so a hydrologic failure mode that would overtop the dam, which could lead to failure of the dam, high loss of life, and catastrophic damages through the downstream populated areas. The preferred alternative was to raise the crest using mechanically stabilized earth structure to increase the freeboard. Note that while the non-structural alternatives are presented, the dam breach alternative is considered not feasible. Specifically, the project is part of a system, and this particular dam provides 85% of available system flood storage with another dam in the area. I apologize, I left out these notes. They're not relevant to the presentation, so just ignore those. So in summary, basically Reclamation, the Dam Safety Office follows federal guidelines, specifically the 1978 Dam Safety Act. We have the principles and guidelines that we follow, the agency-specific guidelines, and the Reclamation Handbook. Reclamation is mandated to reduce risks to tolerable levels. And as I was putting this
Yeah, it's a
presentation
question,
together,
Jules,
somebody mentioned
in the
that mandate
Q&A.
is a strong
If you
word.
could get into that,
So
and
rather,
we did
more
run,
like we
certainly
have
not your
concluded that
fault,
there are no
Joel.
other options.
I appreciate the way you're able to
We have
adapt
to reduce
on the fly.
the
Nice
risks
job.
of our
And
inventory.
good presentation. I did notice
So
you
just in
mentioned earlier
conclusion,
that you
cost-effectiveness
use an
approach
interest
is
rate
the
of
appropriate
2.5% in your
analysis for the
economic
work
analysis. Is
that
correct?
reclamation and dam safety does. I
Yeah,
think I ran over the time. I apologize for the audio issues. Jim, I don't know if we have any time for one question.
Mm-hmm. Yeah, I think OMB has a hand in it too, and why they treat those core projects, the Bureau projects, differently than these FEMA hazard mitigation projects.
That is correct.
I gotta get into
and
that. Thank you very much, Joel. We are running a little bit late
to Katie. I went back and looked at
where
we have it.
quite a while. So why don't we take a 10-minute break?
The interest rate, the rates every year,
break.
And we have justification for why we use that 2.5.
And what we'll be having then is
I'll have to look a little bit further to get a little bit more
participate, so it might be around to answer questions, and then have one final presentation at the end of the day. So see you in 12 minutes at 3:20. Okay, folks, we are running a little bit late here today. Not too late, about 15 minutes late right now. But we have Charlie's presentation we're going to be putting up. So Jose will be coming on a little bit later than we had originally scheduled here. Probably about 15 minutes later than we had scheduled on the agenda. I think Charlie's presentation is important to see. So thanks for coming back.
Good morning. I'm Charlie Cobb. I'm with the Alaska Dam Safety Program in the Alaska Department of Natural Resources. I'm presenting here today Basic Risk Management in a Dam Safety Regulatory Program. I have two parts. Part one will be in this break, and then part two will be in the subsequent break. Again, as I mentioned, I'm the State Dam Safety Engineer in the Alaska Department of Natural Resources. I'm responsible for the Alaska Dam Safety Program. It's really a two-man shop. It's myself and my assistant engineer, Ori Miller, and then we report to Tom Barrett, who's our section chief over the Water Resources section, and we're in the Division of Mining, Land, and Water. So again, there's two parts to the presentation this morning. Really try not to read to my audience normally when I'm in a regular conference setting, but under the unusual circumstances of our virtual conference and we're on a break here, I don't know whether you're milling around the coffee table or not, so I will do a little bit of reading at parts of this presentation so that you don't necessarily have to give it your full attention. But I do appreciate the opportunity to be here, and thank you for listening. So my presentation will include a mission statement, and then I'll talk about the regulatory authority we have in the department and the Dam Safety Program regulatory process. And the important thing to understand is that our whole mission is driven by risk management and risk mitigation. Our whole purpose is to mitigate the risk from dams. It's why we've been authorized to be here. And in order to do that, I think it's important that we get the message out. And that's why I say that my motto is communication is the key to the safety of dams. So the mission statement is, the mission of the Alaska Dam Safety Program is to protect life and property in Alaska through the effective collection, evaluation, understanding, and sharing of the information necessary to identify, estimate, and mitigate the risks created by dams. And again, this is an exercise in communication. All of the information that it takes to design and build and operate a dam is about the flow of communication. Whether you start out with a drill rig and you send them out there to drill a hole in the ground and collect data. There's a geotech on the rig that's collecting and making notes and writing that information down. And that information is transferred up through the engineering channels till it gets to an engineer's desk that has to interpret that information and do a stability analysis. And that has to get translated into design drawings that get translated into operation and maintenance manuals, and so on. You understand how much the flow of information is important to understanding how a dam is designed and built, and that's very critical in risk mitigation. The engineer has to have as much information available to them as possible. The risk managers do. The one thing that is probably the most dangerous thing about risk management is uncertainty. And the more information you collect and the better you can transmit it, the less opportunity for uncertainty and the more you understand your risk. So the key statutes, again, we have regulatory authority. We have statutory authority, actually. The legislature decided that to manage the risk of dams, that they would establish a dam safety program. So it actually gives some definition to the program. It provides for a full-time engineer. I can hire technical consultants to support the program. It also charges me with supervising the safety of dams in Alaska. So I have a pretty broad oversight responsibility. The statutes defines what a dam is, and there's these exclusion criteria. So in our state, it's a little bit different from the national stuff. If it's 20 feet high, 10 feet high, and stores 50 acre-feet, so on. Or number 3, threat to lives or property, which is the risk base. So 2 are geometric, 1's risk base. For example, this lake's got only about 4 foot tall in the total height of the dam, but it stores 2,000 acre-feet of water. So we have broad authority. We have the right of to approve the construction and operation of dams or the removal or abandonment. So if you're going to do anything with your dam, you just about have to have approval for it. Other than ordinary operation, well, even that, we'll talk about that a little bit later. We have right of entry, so we have broad authority to come onto your property with due notice and look and see what you're doing, even on private property. We can determine danger and order corrective actions as necessary. We have legal authority to do that. There's some exemptions with other government agencies. We can enter cooperative agreements, and federally owned and operated and FERC regulated dams are specifically exempt. And then penalties. This is a pretty difficult part for us. Enforcement is can be a challenge sometimes for a regulatory program, and we actually have authority to issue criminal penalties. So if you violate the statutes and regulations in some form, it's a Class A misdemeanor. That's a pretty hard. That's a crime. So we try not to use that anymore than we have to, as a more or less as a I don't like to use the word threat, but it's a threat that's there, or it's a risk to you if it's there. But in any case, my MO for the program has to try to be cooperative. So I try to help the dam owners and operators understand what their obligations are under the statute and manage the program cooperatively, and try to avoid ever having to go to hard enforcement. And I've found measurable improvements in compliance just with a cooperative approach, and helping people understand that they do have a liability and a risk. And when they realize that, generally speaking, they've been very good about coming to the table, getting their information in to get their regulatory authorizations. And we've seen real risk mitigation with some dangerous dams as a result of that. So our regulations, getting into the real risk part, this is the hazard potential classification, as it's called. It's based on FEMA guidelines. Class 1 or high hazard potential is probable loss of human life. Some of the other regulatory programs around the world have some, several different classes of these, like extreme hazard potentials with 100 loss of lives or things like that. The federal guidelines is real simple. If it's probable loss of a human life, it's a Class 1 dam. Class 2 is your property losses, other impacts.
All, as a friendly reminder, if you are on the phone line, please mute yourself. I repeat, if you are on the phone line, please mute yourself. We're getting audio feedback. Thank you.
So have a provision for noxious fish habitat protection. And then class 3 is low hazard potential with limited impacts to rural property. So this establishes the basis for minimum design standards, inspections, emergency action plans, dam failure analysis, irrespective of the condition of the dam or its probability of failure. And then we require periodic safety inspections on a regular basis, or what's also called a dam safety review. We require emergency action plans based on the hazard potential classification, usually for the class 1 and the class 2 dams. And then we're unique in Alaska that we have a multi-part application process for certificates of approval to construct a dam. Then we also have this is what I call a scarecrow. The 93-193 defines minimum qualifications for engineers that design, construct, or inspect dams, basically to try to keep the electrical engineers from trying to design a dam. So there's 5 stages in the regulatory life of a dam, and as I see it, application for new construction. When you construct the dam, we're going to want some information about that. The operation of the dam, which is the normal life of the dam. Unusual activity like maintenance or repairs or remediation, and then closure. And we'll talk about that with respect to tailings dams a little bit more tomorrow at the next break. So there's a couple of different kinds of certificates of approval that we write. What I call for extraordinary activity. If you're going to build a dam, that's not normal. That's extraordinary. If you have to modify it or repair it or remove it or abandonment, you don't do that all the time. And then there's the certificate of approval to operate a dam, which is your normal routine activity. We have a multi-part application process, which I said was unique. The scope of work is included in an initial application package early in the process. We'll talk about that some more at the next break. Preliminary design package is where you go out and do your drilling, your seismic studies, your hydrology studies, proof of land use authorization to build the dam. Detailed design package, you're doing your stability analyses and hydraulics runoff calculations and things like that, using the design criteria that you developed in your preliminary design package. Then the final construction package before you go to construction and before we issue the certificate of approval to construct or repair or whatever type of construction work it is would be the final drawings and specifications. It's sometimes called a bid package. Mark issued for construction. This is important because you want to be able to go in the field and know that you have the most current set of design drawings that the engineer has stamped and has been vetted through the regulatory process. And then demonstration of financial assurance in some cases. After that, we want to see the post-construction submittals, how it was built. Those are real important. Your OM&S manual, your an emergency action plan, and then we'll do a technical review on that. And I'm not going to spend a lot of time on that on this slide. We look at this information, we issue the certificate of approval. You go build it, then you give us your construction review information, and we issue your certificate of approval to operate the dam. So the certificate of approval to operate a dam has an expiration date. It turns over with your periodic safety inspections every 3 to 5 years. And then we issue a new one based on the current OM&S manual and your current PSI. So we put special conditions on them as we need to. Could be operating limits, other stipulations such as a risk assessment. If there might be, it could be this work is related to some kind of a problem, or if it's new construction, we want to see some financial assurance that you're qualified to operate a dam, or in the case of a tailings dam, to reclaim and close it after the operating life. And so it's all about communication. There's a flow of information from the operator to the state with the application content, the OMS manual, emergency action plan, routine periodic safety inspections. And then there's a response back from the regulator, request for more information, review comments on their submittals. We issue our certificates of approval with the special conditions as necessary, and usually a schedule to do emergency action plan exercises and updates. So that's the foundation for mitigating and managing risk in a dam safety program. And I'll get a little bit more into the weeds in the next presentation and look forward to seeing you then. Thank you.
And Preston, you would still like me to show the second video, correct? Even though some are having audio issues?
Yes.
Hello, everybody. Welcome back to your break. I appreciate your divided attention while you get your cup of coffee and try to double duty paying attention to what you have in front of you there, and my opportunity to speak to you during this pre-recorded break. This will be part 2 of basic risk management in a dam safety regulatory program. I'll follow on from what I presented at the first break with a revised mission statement now, and a little more information about the communication, how important it is, and getting into the weeds of some of the regulatory issues. And I think in this presentation, you'll see a little bit more how risk management plays a role. I don't really have a good feel for how this fits into the context of the greater presentation that you're having there, except this is really the front line in risk mitigation and risk management is the regulatory program. And it's also important to note that a regulatory program only represents the minimum standard of care. Obviously, you have to clear the regulatory requirements just to get started, but it doesn't stop you from doing more as a dam owner or operator to understand your risk, to do a better job. In fact, that's your ultimate responsibility, is to do as much as necessary to maintain your dam in a safe operation. And we just represent the minimum standard of care for that purpose. So the revised mission statement of any dam safety program is to protect the life and property through the effective collection, evaluation, understanding, and sharing of the information necessary to identify, estimate, and mitigate the risk created by dams. And it doesn't matter if it's a regulatory dam safety program or your corporate dam safety program. I think we all share that common mission to protect lives and property. And when we realize that's the case, then we can work together towards that common goal. So again, communication is the key to the safety of dams and risk management. It's all about making sure everybody understands clearly what their particular role and responsibility is, and don't get surprised. Surprises are antithetical to anathema, I guess is the right word, for risk management. So I've been told I've had people claim that I have the most strict regulatory program in the nation. I deny that completely. I will say that I may have one of the more transparent regulatory programs in the nation. I've gotten a lot of compliments for these guidelines for cooperation with the Alaska Dam Safety Program. It's been a real asset for me. It helps provide transparency for the program and consistency from one project to the next. It gets into some plain language discussion about the regulatory requirements and elaborates on it. I developed this when I first took this job because I didn't really know what my job was. I had one day of overlap with my predecessor, and it's turned into a real beneficial work product that allows the dam owner to see what his expectations are if he's going to own and operate a dam. It also fleshes out some of the technical issues that serve to help mitigate risk. So again, risk management's inherent in dam safety. It's dependent on the hazard potential classification, which is your consequences of failure, and then your condition assessment, which is an indication of what the probability that you might have a failure is. So your probability of failure is reduced by, in a dam safety program, basically a standards-based approach, the level of detail in engineering, periodic safety inspections, and performance parameter monitoring, and then in risk assessment and mitigation if necessary. So we have key design standards, and starting out with seismic, I like the terminology maximum credible earthquake, which is deterministic, and then your maximum design earthquake and your operating basis earthquake. And then you start to see some probabilities come in with this kind of a design standard when you start looking at return periods. So these return periods are the also called your annual exceedance probability. That's the chances that you're going to have that earthquake. So if you design to a one of the higher standards like the class 1 dam, your probability of seeing that earthquake is lower than if you were designing it to the class 3. So right out of the gate, just in your design standards are baked in certain levels of probability. If you design it to that standard, the chances are if you see that earthquake, you're not going to have a problem. Same thing with the hydrology. My rule of thumb in our regulatory program is that the 100-year flood is the minimum standard for low hazard potential dams. The probable maximum flood is the maximum standard, but it's interesting that that misnomer is not a probability-based estimate, but it's a pretty big flood, so chances are you're not going to see that, and that's not without its own level of discussion and controversy, but that's beyond the scope of this meeting. And then in between is a calculated standard. And then at dams that mines, other considerations may apply, like with zero discharge facilities. A lot of tailings dams don't have spillways. This particular dam is in my backyard, full disclosure. And it didn't fail, I'm happy to say, but it was close. So you saw this in the previous break. The scope of work needed to advance the conceptual design. I want to talk about that for a few minutes. So this is my favorite graph in the world. And I think it really tells it like it is. If you don't do a very good job with your engineering, your chances of having a failure are high. And I think that applies to everything. This does is show you, 5 orders of magnitude in risk reduction by the level of detail in the design. Now this is, again, I have to point out it's for slope failure, for embankment slope stability, but I think it applies to everything. You'd never be able to launch the space shuttle if you did a poor job with your engineering. You have to go to the high level of detail to ensure that you have reduced your probability of failure sufficiently. And then the scope of work. If an engineer cannot write a scope of work, how can there be any confidence the engineer can design the dam? And why would you ever want to do business with an engineer if he can't tell you how far he's going to, what all he's going to do to design that dam? You really can't wing it. You need to plan ahead. So risk management informs the scope of work necessary to design the dam, and it leads to early agreement between the engineer and regulator. That's why I want to see it early in the application process. It shows why it's so important. This is out of an ASDSO class, just showing that you save a lot of money if you can get your agreement of what your design standards are early in the design process. If you wait till you've got 60% or more of your design done and you come along to the regulatory program and say, hey, you should have designed it to the probable maximum flood, not the 100-year flood, it's going to cost you a lot to change that design. And then performance parameters is a unique thing. That should come out of your design. What is it about this dam that helps us to, how is it going to perform? What can we look at to determine if it's performing like it's supposed to? This is becoming a big deal, especially in the tailings dam world. What is it about it that we can watch to see if there's a problem developing? They're also called quantifiable performance objectives. If they don't come out of the design, you want your inspection engineer to start looking for the kind of things that you're going to look for. And usually it can resolve down to some unique aspect of the system. Spillway capacity, deformation limits, operating limits, maximum water levels, and things of that nature. And that all should be included in the operation, maintenance, and surveillance manual. And one thing about that, it should be written for the operator, not the regulator. It's not telling me how the dam works. It's you telling your operators how the dam works, because they're the ones out there that are driving the car. So they need to know how that dam operates. So don't write an O&M manual to me. Show me the O&M manual that your operator is using. And the operator is the front line in maintaining safety and risk. If I'm just the passenger in the car, I don't have a whole lot of control of that car. The risk is, apart from getting run over by another truck, it's on that driver. Even that's on the driver. So whoever's driving is the one that's got the most responsibility for mitigating the risk. And I will not issue a certificate of approval to operate without having an O&M manual of some sort. The periodic safety inspections is the routine operation, for the routine operation. Every 3 years or so for the class 1 and 2 dams, 5 years for the class 3. It's also called the dam safety review. And then tailings dams need annual performance review as well, because they're usually in a constant state of construction and operation at the same time. And you need to keep a little bit closer eye on tailings dams in some cases. And then the condition assessment that we use is from core guidelines, and I really like them because otherwise you get an inspection report and it says the dam's in excellent condition, or it's in good condition, or it's in bad condition, and those kind of adjectives don't have a whole lot of substance to them. The core guidelines have a little more definition to each of these categories. I'm not going to go into it there, but it gives you an idea of what it is. So combined with your hazard potential and your condition assessment, you have some real key indicators of risk right out of the gate. So you can use that to determine what your level of urgency is for your taking some action. Generally speaking, this kind of process is in a non-emergency situation, and you have time to maybe follow up on what you have discovered about the dam with some more other risk assessment methods, or in the engineering design, we may use risk assessment. But in my program, it's not used for a go, no go decision on the dam construction. That's done with the land use authorization. This is just exclusively a kind of a nuts and bolts type of review to get it a good housekeeping label. Couple of different kinds of risk assessment methods. The failure modes and effects analysis and PFMAs are not without their share of criticism. Risk may drive an independent expert review. And I think that recommendations for risk mitigation should be included in the risk assessment reports. And just be careful with your risk mitigation to make sure that you don't kill the patient trying to cure him. I know there's been examples of that happening in some other dam construction projects, but and funding for mitigation is always a challenge. So a lot of times you see a dam that'll sit out there with known problems, and there's just no money to mitigate the risk, and you hope that it doesn't fail. And that can really cause for some sleepless nights sometimes. But I'm glad to say that this particular dam in my backyard eventually got rehabilitated. So this is a unique thing I want to talk about for just a few minutes with respect to tailings dams. It shows that if you can get the water off the system, then you can reduce the risk and closure. And what happens after that depends on whether you did a good job with your design, whether it's just your basic design. Well, if you did a poor job and you take the water off, you may still have to watch it for a significant period of time. The best approach is if you design for closure and you can accomplish geologic stability, and you can eventually, this thing will just settle in to become a landform, and you'll eventually be able to walk away from it. So this information is available to you with at my website. You can download the guidelines and see the dam safety program there. There's the website. Thank you for your time, and hope you all have a great virtual conference there. Thank you.
Thanks, Charlie. Thank you. And I know I'm saying that because I know you're participating now. You're responding to some questions. I apologize for those of you whose limitations didn't allow you to hear that very clearly. You can look at, watch it on the YouTube, and I'm sure Charlie will, you can reach out to Charlie with any questions you have. If you have heard it well, you have questions, put that in the Q&A for everyone, not the admin technical box, but the Q&A for everyone. And Charlie, I'll refer you to that admin technical one because there is a question up there. So without further ado, we're about 15 minutes behind schedule, but let me get our last speaker, a good case study from Jose Bermudez from the Puerto Rican Electric Power Authority. Jose, take it away.
Perfect. Good afternoon to everybody. My name is Jose Bermudez. I work for the Puerto Rico Electric Power Authority and the Dams and Irrigation Division Head and the Dam Safety Unit Head. And I will make very clear, I'm not a FEMA expert and don't pretend to be. I would like to give you this afternoon the perspective of working on a FEMA project under the 404 program from a non-expert view, and trying to provide or getting approved a project that is very well documented. And let's start with it. Okay, the asset that we're going to be talking about is Patillas Dam. Patillas Dam is an earth embankment dam built by hydraulic fill methods. The dam is 147 feet tall from the bottom of the toe and 1,067 feet long. It's located at the north, that's a mistake. North, it's not north side, it's the south side of the, well, it's the north side of the Patillas town, but it's located at the south end of the island of Puerto Rico. This is a very old, it's a 108 old dam. It does have a intake tower with a tunnel which allows to serve water from the lake to the Patillas Canal. The dam provides water for irrigation, power generation, and 2 potable water plants, serving about 100,000 persons to the southeast of Puerto Rico, and provide water for a 400 megawatts of base generation into the Puerto Rican grid. That is a substantial amount of power generation. So it's very important that we keep the water flowing for power generation. In 2015, Reclamation prepared a risk analysis including seismic, geotechnical, hydraulic, and hydrological, which increased the operational risk of the dam. We'll talk about that a little bit along the road. In January 2016, Reclamation recommended a level restriction for operational safety purposes of 25 feet. Now, since this will not allow the reservoir to provide water to its current customers, PREPA decided to lower only 12 feet from 222 mean sea level to 210 mean sea level elevation in order to have an interim risk reduction during its normal operation. And we also have done some other interim risk reduction measure, like increasing the range of the warning system. Now, can you guys, everything is still, I'm hearing, right? Everybody's hearing so far. So in September 2017, during Hurricane Maria, Patillas Dam performed without any major concerns. Only minimal damage was caused by the hurricane. So this was good for all of us. It was good for the dam safety program. But in order to have any opportunity to participate in a grant to get any chance of funding, that was quite a challenge. And that's the story of what we're going to be developing so far. So I'm going to be sharing some comprehensive photos of the dam. This is a view of the downstream of the dam. You can see all the living areas very close to the dam. The dam actually is about 5-minute drive from the Patillas town. So the risk is very high. I mean, you'll see the flooding map. It's quite a challenge. So it also have a spillway with about 90,000 CFS capacity. It have 3 Tainer gates, and the spillway was refurbished in 2010, and it's been performing very well since then. This is a view from the right abutment looking to the left abutment. You can see the intake house. It's the same view, a little bit lower down the road, closer. That is a view walking into the crest of the dam, looking down to the left abutment. This is a view looking to the right abutment. And you can see here on the left corner 2 structures. One, it's a low head power generation, which is out of use, and the Patilla Canal 4 Bay. So this is the structure that received the water from the lake and put it into the Patillas Canal to be delivered around the road. It begins in the Patillas town, and it provides water for 3 towns down to the west of moving from east to west on the south coast of the island of Puerto Rico. This is another view of the dam. Basically, you can see here that we are on a reservoir restriction level. So we lost about 40% of water impoundment. That is a very critical amount of water, and we had to do it just, to operate with a better safe perspective. That's a closer view from the generation plant, and this is a front view of the dam in the access road going into the 4 Bay and the Salish hydro generation plant. Now, here you see the Patillas Canal 4 Bay and the intake, the entrance to the tunnel. Now, this dam does have a tunnel built in the 1913. The original design, the water was received through the intake, flooded that tunnel that you see there, and then there was a weir that flooded into the Patillas Canal. In the 1960s, there was an accident that there was not with the intake inside the lake, so they have to draw down the level, and they prepare a new intake structure, and instead of using the tunnel, they put a 54-inch pipe. So this is a view inside the tunnel. You can see now that the water goes from the intake tower along a 54-inch pipe into 2 limit torque valves that access then the 4 Bay structure. You can see some of the conditions of the tunnel. This is a horseshoe tunnel, which is 20 feet bottom wide. It raised straight 10 feet, and then it radiates 20 feet again in the horseshoe. The pipe that you see here originally is a 54-inch steel pipe that had sorry about my English and my Berry language. I'm trying to break it in here. It had a system to avoid the rust, and we changed that with a pipe wrap system. That was probably in 2008, and it's been performing well. We use a system and then we paint it, and it was quite a challenge, but it's been performing very well. You can see the conditions of the pipe. That was some of the work that we did when we did the pipe restoration. We added a butterfly valve to provide more resiliency to the piping system, since the intake valve on the intake tower was not working well. We have to use a saddle and a flapper in order to cut the water, do this work here, install this valve, and then do the rest of the work. And in front of this valve, we have two limitors that are fully operational. Okay, that's another drone photo from the dam. In the left side, you can see the spillway area. Now, what studies do we have on this dam? What evidence can we provide in order to say FEMA, hey, we have a problem and we need to solve it, and we need your assistance? So in 2014, we did a geologic studies from the Great Southern Puerto Rico fault zones from Guayabal to Abaca dams. That was done by reclamation. It was quite a surprise, because once that study was done, the findings in this geologic study affected more Patillas than the other two dams. It affected Patillas more than Guayabal and Tuabacas. And you will see the FN chart, how it moved forward. We also performed the PSHAS, the probabilistic seismic hazard analysis. That was done by reclamation. PREPA and reclamation have a working relationship for a long time now. In November 2014, we did the Patillas Dam seismic evaluation of the spillway walls and pier. In the 2015, that's when we started getting critical here. We did the flat dynamic deform analysis of Patillas Dam. When that study was done, the actual deformations in X and Y direction were exceeding 20 feet. So it was quite a lot of deformation due to the hydraulic field, and that's when we started getting critical. Then that was used by Black and Beach to do the stability and deformation analysis. And finally, we did the Patillas Dam evaluation risk analysis. And here you can see the flooding area. And if you look a little bit closer in this area here, I could say that half of the Patillas town get impacted by the flooding. As a matter of fact, we got areas for more than 20 feet of water. And the highest building in the Patillas town, which is a very small town, is only 2 feet, 2-story buildings. So imagine what will be the effects of a catastrophic failure of this dam. Now here you can see the FN chart, and you can see that these are most of the most important dams in the island of Puerto Rico. And you can see here how Patillas stands way above of all of the other ones. Now, when Hurricane Maria reached the island, it affected the whole island, and it brought a lot of damage, a lot of problems, but it also brought some opportunities. Now, I'm going to discuss a little bit of the hazard mitigation grants programs and that were available to get funding for resiliency and to repair assets. So basically, we have the public assistance programs, that is for repair or replace damaged elements to its pre-disaster conditions. So this public assistance is for assets that were affected by the hurricane. Then you have the Bipartisan Budget Act that is also for assets that were affected, and the 406. Now, the 406 can be used for assets that were affected. Now, Patillas, fortunately and unfortunately, were not heavily affected, or were not affected at all. It was minor by the Hurricane Maria. So the only chance we have was a 404 mitigation program. That's the only program that will allow assets that were not actually damaged by the actual event to qualify. But there's some tricks to get your asset or approved. Now, the difference between both the 404 and the 406. The 404, the states administer the program. The funding is limited and is competitive. The sub-applicants prepare applications, and as I just said, undamaged facilities are eligible, and there's a 25% match required. The entire state, in this case the island, participate in the program, and this is a very interesting factor here. Work started before approval is not eligible. We will talk about that a little bit there. Now, why we talk about sub-applicants here? Okay, in Puerto Rico, the government is the applicant. So we have the office, the Central Office of Recovery and Reconstruction for Resiliency is Core 3. They are the actual recipient. And we, the government, the rest of the government agencies are the sub-recipients. So everything have to go through the Core 3 office. Now, in the 406, the difference is the FEMA administers the program. Funding is disaster-based. FEMA can prepare the applications, but only damages facilities are eligible. It's better financially because you only have to put a 20% match, and it's only for disaster-declared areas that can participate in the program. Well, how we were able to get patillas in this program. During the hurricane, I started, we had a major emergency here with Oaxaca Dam. So every time I had a meeting with FEMA to discuss Oaxaca, I brought up Patillas Dam and the issues that we have with them. And I provided information. I ended up making about probably 3 or 4 presentations to the FEMA people, and they recommended to me, Jose, with all that you have presented to us, we said that Patillas Dam is a very classical example program project for a 404 mitigation program. So when the opportunity came on, I started pushing into my agency, and I was able to submit the project to the 404 mitigation program. The highlights of the 404 program. Funding is used to provide protection to undamaged parts of facility or to prevent or reduce damages caused by future disaster. The whole island or state, not only the area where was declared the disaster. In Puerto Rico, Maria was in the whole area, so that's not an issue. May qualify for 404 mitigation projects. The 404 grant is managed by the state on the funding provided in the Stafford Act. The key purpose for this grant program is to enact mitigation measures that reduce the risk of loss and life and property from future disaster. The states, basically, the government, receive a percentage of the total federal share of the declared disaster damage amount. That's probably, they receive about 20%, which is used to fund projects anywhere in the state, regardless of where the declared disaster occurred. The 404 grant may be used in combination with 406 program. Due to the Hurricane Maria event, Puerto Rico received a total of $3 billion hazard mitigation grant program funds, require a matching of approximately $1 billion for a total of $4 billion for the 404 hazard mitigation program. Now, when the notice of funding availability occurred, the Central Office of Recovery and Reconstruction for Resiliency emitted the notice of funding availability, or NOFO. We submit the letter of intention. Core 3 process and notifies the sub-applicants of the recommended selected proposal. So, like I said, it's competitive based. So we have to provide a letter of intention with our project, and the government basically decides which projects are going to be eligible. Now, once that project is eligible, you will receive an audit, and we will have to prepare the whole letter of invitation within the FEMA process, because once the government say, okay, FEMA, these are the projects that I want to develop on the 404 programs, FEMA will manage the rest of the process. So once that happens, FEMA reviews and make determination, and it starts, I call it the Game of Thrones, where you have, there's a lot of requests for information, and you have to prepare all the information. And this is the challenge, at least for me, it was a challenge, because even though I had two consultants for this process, but your consultant have to talk the FEMA language. I mean, it's we had a very documented project, but you have to put it into the FEMA language in order to get it approved, and you have to follow the grant rules. That is basic. If you don't have that, you're gonna have a lot of trouble. And I was struggling a little bit, and I'll discuss that a little bit further on how we overcome that. The approval criteria. The projects must conform to both the state and local hazard mitigation plans. Project must provide a beneficial impact on the disaster area. The project must be in conformance with the 44 CFR Part 9 and meet all applicable environmental and historic preservation requirements, laws, and regulations. Remember I said this is a 108-year dam. This is an historic dam, so that was an issue. We will talk about a little bit further. The project must solve a problem independently or to be functional portion of the solution where there is assurance that the entire project will be completed. And the other challenge, the project must be cost effective. Now, letter of application, we have to provide a scope of work, a schedule. The schedule have to be in a period of performance of 3 years. So what are we proposing? We were proposing two alternatives. The first alternative will be an overlay on the existing dam that will extend approximately about 400 feet from the toe, and it will be earth-based, and it will increase the crest about 20 feet with all the filters and all the safety criteria. The second option will be a new dam in a new footprint downstream based in a roller compaction concrete. So we have to provide a cost estimate for the project. We have to do the cost effectiveness. We have to provide an environmental and historic preservation compliance. And in this project, that was an issue because it's an old dam. Supporting documentation for technical feasibility, compliance, and cost effectiveness. So it's not only providing all of that information, you have to provide all the backup for that information, plus all the assurance forms, which are basically the forms needed that you need to fill out in order to comply with the system. Now, why I said cost effectiveness. We basically work with two requests for information. We provided the first letter of intention, which was very, very robust. But when it came to the cost effectiveness, the consultant that I had didn't have an specialty on the cost effectiveness. So we ended up doing the cost effectiveness by ourselves. It was an electrical engineer that had a little bit of understanding on working with the FEMA program for cost effectiveness, and I provided some of the information. We came up with a cost effective ratio probably about it was over 1. That was not going to cut it, but we received a second RFI, and again, my consultant at that time didn't have the right support for the cost effectiveness. So we ended up doing the same, and I was very worried because we provided all the information, all the narrative, everything was looking very good, but the cost effectiveness. And the other issue with the cost effectiveness program that affected me, and I will tell you later how we solved it, it was the earthquake. Now, the FEMA does have a way of doing the cost effectiveness. It provides a cost-effective a benefit cost tool for performing the exercise. This tool allows for the creation of a benefit cost analysis. Within the tool, there are many modules by project type and natural hazards, such as floods, hurricanes, safe rooms, earthquakes, wildfires, droughts, whatever. Now, even though we are doing dam restoration, the flooding caused by the dam, it was because of an earthquake due to liquefaction. So we have to use the earthquake mode. And that was a tricky part, because when it comes to the earthquake, they ask you, okay, what is the recurrence period of the earthquake that may cause the damage? The first answer that I provided on my BCA, I went to the Puerto Rico Seismic Network. I looked for information where they say that the recurrence of strong seismic events in the island were close to the 100 years. FEMA didn't like that answer, and I was a little bit misguided. I mean, I had no experience about that. So when the second request for information came, I hired another consultant that was an expert in the FEMA grants and managing the cost effectiveness. And that's when the game started, the started shifting to our side. We prepared this cost effectiveness analysis, and I provided the whole cost effectiveness that we submitted for the project here, because we have a lot of explanation just in case anybody is interested on how we did the narrative. But it's not only what you see there. There was a lot of information provided there. Now, we were talking about recurrence events. Now, when we came to that part, I initially said 100 years, and my expert said, well, Jose, you don't have to do that. If you have the pictures from reclamation, let's go and see what the report says. And it was so critical that the lowest seismic event, recurrence event that we have in that study, it was a 200-year-old. You know, the lowest recurrences mean that the chance of occurrence or probability of occurrence is higher. It's a 200-year, and we used the 200-year events, and we provided all the information for the backup for that. And then when we started making the benefit cost analysis in the right with the right approach. So there is all the narrative that we provided. Unfortunately, I cannot provide all the information that that we provided with that benefit cost analysis, but I will discuss a little bit here about what is in each section of this document and what we provided in order for backup documentation. Basically, the first section is the property configuration that will include location with coordinates, type of hazard to be mitigated, type of property, type of analysis, which is using the BCA, which is the cost damages. In the one prepared for Patillas Dam, we use professional expected damages. The second section is the cost estimation that will include the project cost. The useful life in the Patillas, we use the default of 50 years that was provided in the actual tool. And the annual maintenance cost of the proposed retrofit. The third section includes the damage analysis parameters, which is the ratio between the year that the asset was analyzed for a BCA and the year the asset was built. Fourth section, utilities property, description of the type of utility, customer served, and the value of unit served. For potable water, we didn't use the default amount of $88. We use per person per day, we use 114. Fifth section, we use the professional expected damages before mitigation. That's where the recurrence for the seismic event was asked, and we provided that 200-year. And they also provided an estimated impact days due to a catastrophic dam failure. Cost of optional damages as benefit. In this section, we included detailed explanation about the amount of customers saved by Patillas Dam and the consequences of losing the dam as a source of potable water. It also includes impacts on power generation costs in case of catastrophic dam failure. Includes the time needed to put a water delivery system in place in case that the event is not complete, it's not catastrophic, and we don't lose completely. We don't complete. I mean, we kept the dam, but we lose the capacity of providing water from the dam to the canal. And we also provided an estimated cost to fix the scenery of damages of the dam, which prevented water extraction. There was a lot of work done. Now, some of the information that we provided, like we use all the loss of life. There is a big value on FEMA for the loss of life. We have the loss of life study, so we provided all the loss of life that added to the damages. We also use for the generation. Okay, as I told you in the beginning, Patillas Dam provide water for a 400 megawatts plant. If we lose that water, the plant does have a backup wells, but the problem with the wells water is that it's very hard, and they already have problems within their system. So they can use the wells for 4-5 days, and if they extended the use, they will have operational issues. So that's why it's very important. I talked to the PREPA personnel to give me an analysis. If we lose those 400 megawatts from that plant, which is a coal-based plant, and we have to change that generation instead of using coal, which is cheaper, from a more or a higher cost fuel, what will be the impact? So that was a lot of $1 million. So that added also to the damages. So municipality, I talked to some friends in the municipalities, and we had all the assets costs from the municipalities, and we provided maps showing those assets, where they were located in terms of the flooding, and that also added. So basically, the standard mitigation benefits was $3,248,543,469. The cost of the total projects was close to $560 million. So we came up with a benefits cost ratio of 5.76. Very different from the 1 point something I provided in the initial cost benefits analysis that I did without having the right guidance. Now, final recommendations: have all project documentation available and digitalized. Have a good GIS consultant. Make sure to have all channels of communication open within the recipient, which in our case is Core 3 and FEMA. In Puerto Rico, the Puerto Rico Electric Power Authority is the dam safety regulator and also owner. These situations did not affect the grants application process. Make sure that your consultant knows the FEMA process and have a very well understanding of the process involved in the preparation of a benefit cost analysis. Networking. Make sure that they have a good networking within FEMA and the recipient agent, which is the Core 3. Make sure you have a good communication with the rest of your dam safety consultants. You may require information, certifications, or other information from them. Always have a fresh set of eyes that can review the information you are providing and be open to suggestions. Provide all answers to FEMA requests for information in the time proposed. If by your standard you need additional time, request it on time. Do not wait until the last minute. Usually they are good at it and they will allow the time if you request it on time. And last but not important, provide backup documentation for all information provided. Now, there's a reference guide for BCA in case you guys are interested. If you take a look at it, make sure that you take a very good look at Appendix A. It will give you a comprehensive guideline if you need to prepare one of these within FEMA. I don't know if I was fast or I was slow. I was the last today presenting, so I hope I didn't bore you with my presentation. And as I told you before, I'm not an expert. I just give you my perspective. Two important things. This project have not been approved yet. It's on the pipeline of FEMA. I'm waiting response. And if I don't get the approval, I will go to the appealing section. But I'm very confident that we will prevail and that it will be a benefit for all the people of Puerto Rico. I hope this information that I provided here will be of any benefit in the near future for any of you that may have to go through this process. And thank you for the opportunity.
Nice job. That really was a very good presentation. I really likened your analogy to the Game of Thrones process. We do have a little bit of time. You did get us a little bit back on schedule, so appreciate that. You've got some comments here in the Q&A, really essentially complimenting you on the great presentation. Do you mind if I ask you the cost of the BCA? You mentioned consultants and you're sort of a stop, in your initial efforts. Do you have?
I was too fast. Well, I think I gave you. That's quite a challenge to pronounce the amount of the cost that we provide. I can move back a little bit here. Okay. You're talking about this the total standard mitigation benefits.
The cost
or total cost
and your consultants to do this analysis and to support your.
The cost of the consultant. Well, I don't have that information. Let me explain why. Within PREPA's organization, there is an office, it's called the DFMO, is the Office for Management of FEMA funding projects. They are the ones that manage all the consultants, and they are the ones who, hire them for you. You don't have a way to choose. Now, since I was so desperate with this, I was able to look for outside help. And I have to give the same for a lot of people that were critically in here, like Andy and Bill from NIPA. They will be like under an MOU with PREPA. They are, I don't mean to upset anybody, but they have a lot of gray hair, and I like gray hair. They have a lot of experience, and they helped me a lot of building this. They complemented the work of the original consultant that basically was providing the information that we gave them. So I didn't receive too much feedback from the grants from them. Now, I would like to thank you, Maria Judith. She helped me. She is an expert. She knows the grants very well, and she was the one who basically gave me the hand. And it was just a help. I just thanks that she gave me the help, and we were able to provide all this information. And as I told you, I have no answer so far from FEMA, but I'm very confident that we will prevail, and this will be of great benefit to the people of Puerto Rico. I don't know if I was able to answer, but that's the current situation of the project.
For sure. And again, I encourage you to take a look at the Q&A. A lot of folks were really pleased with your presentation. The one question I did get was early on in the presentation. I think you talked about lowering the reservoir. Question the person had was, why was it recommended by Bureau of Reclamation that the reservoir level be lowered by 20 feet?
Oh, okay, great. That's a good question. Okay, when we did the analysis, when Reclamation did the deformation analysis, after the deformation, there was a certain amount of freeboard, like the current crest elevation is about 230, and you reduce about 20 feet, 20 to 25 feet of that, there will be a certain amount of freeboard. I mean, amount of freeboard that is all cracked up, all deformed, that will allow, there will be water flowing through. But what we're looking is to try to gain some time for warning, and at the same time that we don't have a water level higher than the available freeboard, because then the water will the overtopping will be immediately, and the catastrophic failure, I mean, there's no time. Now, how much time of warning we will have if that's happened? Who knows? I mean, if we are able to have, if we have an event, a seismic event of the magnitude of enough magnitude to have that kind of deformation, I think that what we're trying to give is the information of the people. Like, if you get a shake that you cannot, you fall in the floor and you cannot stand, you better get out of the flooding zone. I mean, that's that out of the flooding zone. I mean, that's that. That's the big challenge here.
So I guess, as I understand it, so the Bureau recommended 25 feet. I think you temporarily lowered it to 12 feet. Is that correct?
That's right. But the problem is that this is the most important and the only water source for all the southeast. I mean, and if I lower 25 feet of water, the amount of impounded water, you know, we will be in a drought and we will be in a crisis continuously. So we have to make a balance. Now, in 2020, it was a year that it was a challenge for everybody. For us in Puerto Rico, we started with a 6.4 magnitude seismic event, which started on the right in the south coast, but at the west coast, in the area of Yauco, and there was a lot of replicas within that. And we have to act within all of our reservoirs, watching them, observing them, and I hired a surveyor to check our alignment points. And we, in Patillas, I put 24-hour watch, and we did 3 surveying alignments with all these events. The dam, which you could feel the shaking. Actually, we were drilling in the dam to get the geotechnical reports, and I have to suspect the drilling process because all the drilling crew was scared because of the aftershocks. Now the dam didn't deform horizontally or vertically, and we still watching. There's no leakage. She's not leaking. In 108 years, she doesn't have a leak, so she has performed very well so far. But unfortunately, if we have a event strong enough, I mean, it's gotta be that event, we may have a catastrophic failure. But with the 6.4 on the southwest of the Puerto Rican coast, we still have a standing dam performing well.
Again, thank you for the presentation. That concludes us for today. We're just ended up being 15 minutes over schedule, so that's not too bad. I want to thank you all the presenters today. Really, it was an outstanding day, outstanding job. I learned quite a bit. Also want to thank the technical staff behind the scenes, Danny and Christina and Alicia, for making my job here so easy. So I guess we'll be seeing you all tomorrow.